It's like
No,
yes.
it's not Google.
Google.
I'm not directly
Stolen from Google.
You're contracting at Google? Oh.
Yeah, which is yeah, we're working with
All right, cool. Thank you. So welcome. Welcome to CSTU. So welcome to CSTU. We are here to learn AI and TensorFlow. I'm looking at around 8 weeks. We are going to be together every Saturday and Friday and Saturday. Friday 7:30 to 10:30.
Yes.
7:30 to 10:30 or so. It will be online. So we'll be all logging in from home, and it will be more or less lecturing and following up on homework and any logistics we may have for 3 hours on Friday. And please try to attend the courses. Don't be absent. It's very important because if you miss one class, then it will be very difficult for you to catch up next day. Then Saturday we will come at 1:30 every Saturday afternoon. We'll go until evening, like 7:30 or so, right?
Right.
So that's a long chunk of. But this is where we'll do a lot of hands-on work. So that's our schedule. Did Dr. Glenn share home syllabus with you?
Yeah. Okay. In a group, you're in a group too.
Okay, so the syllabus has been already been shared with you. So this course, as I said, it will go on for 8 weeks, less than one Friday. So we didn't meet yesterday, first time we're meeting today. So 8 weeks, we have 2 homeworks, a midterm and a final exam, and a project. Okay, so we'll all work on a project. So that's what the course content is. And the topics, we'll go through that later once we are done with the introduction. So that's the content of the course. You can work, we have around 11 students or 15 students in the class?
It should be around 15.
Yeah, so we'll work on a project in a group, okay? So make a group of 2 or 3 people, okay? Depending on what you want to do and what size of the project you want to work on, you can have 2 or 3 people. So usually I always say that if you are new to this topic and somebody knows a little bit about it, kind of mix up together. So we all can have a high performance team. I always believe in high performance team. And when we have right ingredients in a team, we can be a high performance team. So that's a project. So you start thinking about a project. I'll give the requirement of the project later today. So you can start thinking about what you want to build. It can be a already done project on SlideShare or you want to do something original depending on what you want to work on. You want to build an application, you want to work on a project proposal. May not it's essentially you have an app ready, but you have a concept. So you want to collect the requirements and see how it can be built. So think about that. The homework, I will post first homework this week, but it's not due until half of the class is over. So 4 weeks from today. The homework will be due 4 weeks from today, but you can start working on it slowly as we pace through the course. Because we're going to meet every week. It's going to be good for you to ask questions on the homework. And then we have a midterm at the end of 4 weeks. Midterm exam will be here on a Saturday. My midterms are more non-objective. So usually I put in cases, applications, and more or less industry applications. So you will learn how things work in the industry, right? So that's the goal of this course, not necessarily just theoretical study, more applied. Okay. So my midterm maybe a little longer, like what you were discussing. You do here, and then you take it home if you want. You can take it home and complete it, because I always see that students, if they have more time, they really pay attention and do it right. So so you submit what you do in the class, and then you take it home and complete it, because my exam tend to be a little longer. Okay. But I will make sure that it's relevant content as the industry practice. Then we'll have another homework at the end of 4 weeks. I'll post another homework. which will be due after the end of the class. So it will be due end of the class. And we'll also have a final exam, okay, and a project presentation. So we all will come and present your work, like as if you are presenting to a manager, okay? So that's the content of the class. So this AI field has been a big hype over last few years. Last year has been a big deal.
One question.
Yes.
Are there any specific software applications?
Yes. So I'm getting there. Yeah. Okay. So so that's a good question. So let me answer his question first. So I'm a big proponent of cloud environment. Okay. So because I don't want to spend time in the class installing software, and AI and packages that we have in AI tend to be very convoluted. Okay, package dependence. You're using Windows or Mac, and there's so many things going on. So I mean, when I started teaching this last year, we were spending 5 hours just installing software, and some students are already advanced. They already have everything set up, and so I usually use cloud, okay? So you all will have a Jupyter notebook hosted on AWS, which will have a GPU instance. So it will have graphic processing unit running on AWS. Each of you will have your own IP address. That's your instance. So while you're here on Friday and Saturday, you will have your AWS instance running. After that, every time you come, you will have your AWS running. If you want to use it in the meantime, right, then I will give you the AMI address. So if you have an AWS account, you can run it on your own, however long you want, right? It costs around $20, around $20 for a day, right? If you run it full day. But if you use it, shut it down, then start again, it'll be a few dollars, maybe $3 if you run it for 4 or 5 hours. So, so I'll give you the address of the AMI address, so you can spin your own. I'll show you how to do it. So if you have your own account on AWS, you can run it anytime you want. It will have everything ready as you had in your class. But when you are here, I will have it ready for you, okay? Each of you will have your own account and Jupyter notebook that you can use, okay? So that's the AWS software. Everything will be on Amazon AWS with a GPU instance. They have a TPU, which has like the latest NVIDIA GPUs on it. So that's the NVIDIA Titan GPUs running on the cloud. So you will have full accelerated environment where you can run any AI application, right? And we'll share the code. And you will feel that we'll run one without GPU and one with GPU. You'll see the difference, okay? Big time, right? CPU versus GPU. So we'll talk about that. So that's logistics of the class. Thank you for asking that question because that's very important. So you don't have to worry about installing software on your computer. But then I have students who tell me, oh, I want to do it myself. I want to install everything myself. So I really respect motivation and enthusiasm. So I will share with you the instructions on how to install it on your computer, okay? So you can install it on your computer, and there'll be a lot of troubleshooting. It will take your time. So you will take it home, the instruction, do it yourself, or you can do it in the class. After the class is done, I can help you install it, okay? But I have to be you have to be very careful. It won't work the first time because there's so many packages, and we don't have GPUs necessarily. This computer has the Radeon GPU, right? This is like $5,000 computer. So it's going to have everything, right? Because I work at Apple, I get the best of the best hardware, and it will run like AWS on my computer, but it may not run on your computer, right? So you have to be careful about that, okay? Because AI needs GPU to run, okay? Because it's brute force. Okay, so do we have all the students, Dr. Ben?
Pretty much.
Okay, so what we'll do is we'll introduce, each of the students will introduce themselves. I want you to answer 5 questions. Tell me about your name, your background, right? right? No, I don't need your age. Your name, your background, your software background. I mean, from 1 to 10, how would you call yourself as a programmer or coder? Then I want to know, why are you here, right? I want to know what you are looking for in this class, okay? And where do you see yourself in after completing this course? What are your goals, right? I want to know these things, so that I can adapt this training based on your expectation, okay? Because this field is so vast, we can't cover everything, right? I want to make sure that I'm meeting your expectation and exceeding it, right? That's my goal, right? As an instructor, I take it with pride that I'm able to exceed my students' expectation. Okay, so maybe we'll start from you. So please answer the questions.
I'm Ashwini, and basically my background is into software testing, quality assurance, and I didn't do any coding as such, but I'm interested in coding. I learned Java, core Java, and little Python, Perl. But since I didn't use for a long time, so I already forgot, and now again I refreshed in the last session.
Oh, best of luck.
Yeah.
Okay.
So I know this much. I mean, just basics.
Okay.
Yeah.
And what is your expectation from this class?
To learn about AWS and deep learning. I'm interested to get into the AI field.
Oh, great.
Yeah.
Oh, very good.
The most happening thing in
Yes. Yes. So what are you looking for at the end of this course? You would want to become an expert in this area or explore this further, right?
Yeah.
So you get, okay. Gentlemen.
Okay. My name is Lee Jones. I'm a technology consultant. Right now I'm acting as CEO for a blockchain CIO startup. It's based out of Hong Kong and Washington, D.C.
Cool.
I've been a technologist for a number of years. I started programming when I was a junior in high school in 1965. So I've programmed most of the existing languages on most of the existing platforms that have been around. I've worked on the development of some of the programming languages, particularly Occam for parallel processing computers. I was a Silicon Valley CIO for 20 years and an international award winner.
Wow. Wow. So what's your expectation from this class?
Well, I want to keep current. As always, in all things related to technology. And I think that's important for me as a CEO to have that understanding when I'm talking to my own technical people and when I'm talking to investors.
Right, great.
My name is Simon Ma. My background is computer science. Most of the time is working at CAD. Like we Cadence systems for so many years. And
I was at Cadence on Tuesday giving a talk on blockchain with the IEEE Computer Society. So I was in your auditorium, in the Cadence auditorium in San Jose.
I don't have that much programming experience. I wrote a few skill language, wrote some programs for CAM.
Computer-aided manufacturing. CAM. CAD-CAM, right. Great. And what are you looking for from this class?
Just to get to know AI.
Very good. Yeah. Okay. Yeah, thank you.
So, my name is Linda, and I'm a hardware engineer. And actually, I don't have too much about software background. I don't really do much programming in my job.
Okay.
But I come to this course because I'm working at IT company. So I'm looking for maybe something I can do.
Oh, great. Very good. All right. Yes, ma'am.
Hi, this is Amy. I'm recently graduated from 6 University with a bachelor degree in business analytics, and I don't have much experience in programming, and I just started learning Python programming. And from this class, I just want to know something about deep learning and one step closer to the computer science.
Great. Okay.
My name is Huan Zhang. I just graduated from UC City University and I got my PhD in computer science. My previous research area is about data visualization. I'm very interested in AI and machine learning. Yeah.
Great.
My name is Sophia Zhuang. I have been to years that I learn also know the concept of application usage. So
Great. Great. That's great. Yes, ma'am, in the back. Yeah, I asked like a few questions. Can you introduce yourself?
my name is Wang Chen. My background is bioscience.
Okay. Great. Great. Okay. All right. Yes, sir.
Tony Wang, I've been a software developer for 20 years, mostly Java, basically myself. So AI is something very new, so I'm
Great.
everything related.
Very good. Thank you.
My name is Charles. I work in a utility company, a Java programmer, and I feel maybe I can find some application for the utility company.
Okay.
Yeah, that's basically.
All right.
Yeah.
Great. Yes, sir.
My name is T, and I was also the hardware engineer. I design chip, and for software, I was working. I'm familiar with the C++,
Okay.
some Python, and some CUDA.
Okay. Very good. All right. Yes, ma'am.
Yeah, and the reason I come here to learn AI is I want to export my knowledge.
Great.
And new field.
Great. Okay. Yes, ma'am.
My name is Xia Zhong, and I'm a physical design engineer in the semiconductor industry. And I have computer science background, but most I dislike script and and
Okay.
I want to learn AI because this is the future.
Yes. That's great. Thank you. Yes, ma'am. Yes, sir.
My name is Jack Key, and my original degree is double E. My recent job is to use software to test hardware. And come here for learning AI. Hope to
Great.
find some
Great.
job to do.
That's great. Yes, sir.
Name's Len, and most of my career is spent doing support. I was in service management, and then a few technical marketing roles in the networking industry.
Sure.
A lot of it was routing protocols. And most recent job was with Bhairav in software-defined networking group, and that evolved into a software test role.
Sure.
So we started using Python for automation.
Yes.
We used the robot frameworks,
Yes.
keyword-driven.
Sure.
And now I'm just trying to upgrade my skills and
Great.
further my knowledge.
That's great. All right. You're in the right place.
Yeah.
Thank you. Yes, sir.
My name is Daniel, and my background, I did some software development before, and then
Great.
Java and web CRM development.
Okay.
And then I moved into networking IoT. And the reason for taking this class is really like the next step in IoT.
Yes. Oh, yes. There you go.
Yeah.
That's the right place. Okay. Okay. I'll let her settle down, then we can introduce. Okay. So this is myself. I'm a data science manager at Apple. This side is very old, but I'm an academician. I mean, I never leave school. I'm always learning something new. So I've been working at Apple for 8 years, doing different type of work. 8 years back, when Steve Jobs was still alive, I was doing warranty accruals for Apple as an analyst, right? For more forecasting, machine learning type of work on finance side. And after that, I was working on fraud when Apple grew so fast. There was a lot of fraud in the company. I was applying machine learning to identify fraud in the system for a year and a half. And then I worked on product diagnostics for iPhone. So when you go to an Apple store, they run diagnostics on your phone. So I developed most of those tests. So now it's being used in the stores. I've worked there for 2 years. And recently there have been a lot of issues with iPhone batteries. So I'm a data science manager. I have a small team of data scientists. I'm hiring 2 data scientists right now. If you're interested, please send your resume. I'm hiring right now. So I work. I apply AI deep learning on iPhone battery usage to predict battery performance and how we can improve battery design to improve user experience. Right. That's our goal.
And not intentionally degrade it.
Yeah, so that's so the algorithm that throttles the battery, me and my team designed that. Okay, so it's application of AI deep learning today. Okay, so that's what I do currently at Apple, and I have a lot of strong mathematical background. I have a degree in statistics from Cornell University, an MBA, and I'm almost done with my computer science master from Georgia Tech. I have been teaching for last 4.5 years, so 5 years. Before that, I have taught in university setting, but applied. I started teaching 4.5 years back when the open source technology just floodgates were open 4 or 5 years back when Hadoop came through and then Spark, and you saw all the open source R Python. Last year, year and a half back, we had TensorFlow come out, and we had Theano, Keras, Cafe, Torch, you name it, right? All these open source technology came out of technology companies like Facebook, LinkedIn, Google, and Apple, and others. So I've been teaching that for last year and a half. I've taught around 5,000 students until now in the Bay Area, in Chicago, in New York, Seattle. So I've taught in different places. I teach in a lot of universities here also, like CSTU and others. So I have around 15 years of experience as the US economy evolved from Rust Belt to Silicon Valley. I have moved through all those industries. So I worked for Ford Motor Company for a few years as a statistician, then semiconductor industry like Philips Semiconductors and Qualcomm for around 6 years, doing data science in the fab in Taiwan and here in US, in San Jose and San Diego, and last 8 years at Apple working on different problems, okay? So I want to share my experience with you and my knowledge, okay? So how the opportunity has changed over time for humankind, right? I always start with this slide because we all are here for opportunity in this country and in this world, right? So we have gone from hunter-gatherers to startup founders, okay? So today, most of the innovation and most of the opportunity are created as startups in the Bay Area, okay? And other places also, right? So we have evolved from being oil drillers, from industrialists to financiers, and then startup founders, okay? So we want to make useful things faster than a corporation. So now what we are seeing is all these companies are becoming so big because why are startups are turning into a unicorn, okay? Unicorns are companies more than $1 billion valuation, okay? More than $1 billion valuation. How is this happening? The product life cycle is shrinking to a point where there's a new product, new operating system, new features being developed even in few weeks. There's a lot of demand for it. The product life cycle has shrunk to from years to months to few weeks now. That's why product managers are so much in demand, because product managers are able to get the features running in a short period of time, okay? And then data scientists are important because all these features get added. Now we want to make sure that they are working right. So all the logs are created. People use the features. Logs are created. And we need data scientists to analyze those logs, apply machine learning to improve the performance of the products that are being generated, okay? So unicorns are generated because there are new ideas, new product, new companies, right? And people start using it. The cloud is so mature that you can deploy all these applications on the cloud and it accelerates usage, because once it's on the cloud, it's an app store, you download it, use it, usage data is created, Now, all this data needs to be analyzed, needs to be make sense of, right? And to be used to improve the application or create new applications from it. So we are moving from website to web applications. Web application is user data. Users create data, social networks, right? Or you're using self-driving car. Your car is now an application itself, right? So all those things are generating unicorns from all of these industries: media, mobile, social, cloud, big data, enterprise, e-commerce. All of these industries have innovations, okay? And that creates unicorns, okay? So if you see from 1917 to today, how the industry has evolved. If you see, go back to 1917, except AT&T, no other company is still in the top, right? All the other companies have changed. So we have a more resource-based economy to digital economy today, okay? You see the market cap of top 5 companies, right? More than $5 trillion, right? It's all digital economy, right? That's driving the market today, okay? So all these companies are moving towards AI. All these companies are moving towards the next big thing. 5 things today, okay? Self-driving car, chatbots, agents, right? You name it. And then we are also moving toward decentralization. All the central cloud will not be there anymore because of the IoT. Everything is becoming decentralized. So when the cloud comes down, it becomes a fog. It's fog computing, right? Edge computing. That's where we are at. And these digital companies are driving change today, okay? Driving change in every industry, you can name it, okay? So what happened in 2017 in AI? 2017, Microsoft acquired deep learning startup Maluba. Maluba was one of the biggest acquisitions of Microsoft for $500 million. They bought the company. They are good at audio, voice recognition based algorithms. Google Cloud acquired Kaggle. Kaggle is a competition website. SoftBank bought a robot maker Boston Dynamics, which famously does not use much machine learning, but it's robotics company. Facebook bought AI assistant startup Oslo. So you saw a lot of AI come out of this Oslo. Samsung acquired Fluently, that turned into Bixby. That's on the Samsung phones. And there were quite a few acquisitions like that. You see, these are all the acquisitions. Google acquired all these companies. API.ai became Google Dialog, right? Then you say Timeful, Jetpack, EMU, DeepMind, that turn into the continuous voice recognition that you see today. Apple acquired all these companies. I do a lot of development in this platform called Turi, right? But Apple bought all these companies that turned into iPhone 10. All the AI in iPhone 10 is from all these startups, okay, that Apple bought. Facebook bought all these companies, and now they have all these applications that's eavesdropping on what you're talking about, right? If you have Facebook Messenger, it's listening to you. Yesterday, Walmart filed a patent to see what customers are talking while they are in the store, right? What the employees are talking. So that's all of the acquisitions that have happened. Biggest is surprisingly Intel. Intel bought Movidius, Nirvana, Safran, Mobileye, right? That's like $100 billion of acquisitions in just AI in last few years, okay? So these are all the acquisitions that have happened in last few years. So all this is driving change as we know it, okay? And these are the predictions for 2018. AI content creation, because AI content creation, my friend, he just retired at the age of 40 after he created a lot of content for AI. So he worked at a lot of these content creation companies. He's a digital arts person. So he had cameras in his high-def cameras in his car. He would move around Bay Area. He collected almost 7 petabytes of videos, high-quality road driving videos. He sold it to Tesla, and he retired, right? So AI content creation is a big deal. How can you create high-quality content so that they can be trained? So when I was helping a startup a few years back, 2 years now, they were trying to train on voice recognition, but there was no good quality content to train on, right? So they went to AT&T. AT&T said, we need $100 million. We can share with you high quality audio content with labels, right? They went to Verizon. They also asked for a lot of money because the high quality content is missing in AI. So that's 2018. Rise of capsule AI. We'll talk more about capsule AIs, okay? Facial recognition will be the new credit card, right? Your face is unique, so it can be used to unlock a lot of things, right?
Even iris scanning.
Yeah, AI leveraging.
All kinds of biometrics.
Yeah, AI leveraging offline data, because nobody wants to share their personal information on social network, on other areas, right? Because that's becoming very, very important. GDPR is one of the most important topics these days. How can you make your data private, right? So this offline data means that whatever you do on your phone sits on your phone, doesn't go to the cloud or any central repository, and it gets purged as soon as it's done using it. Like Apple never shares information with anybody. They believe in privacy. We don't have any products that shares information in the public. And it's very, very important, even for employees, for me to get information. Like I analyze a lot of logs for my product that I'm building today. I have to go through like 25 different clearances before I get an anonymized data without linking any customers, okay? So offline data is very important. The rise of on-device AI, Core ML, on-device AI. So the hardware needs to support that. We have a lot of hardware engineers here. So hardware needs to support offline data, on-device AI, right? We'll be talking a lot more about that, right? How can you run AI on your phone instead of going to the cloud or going to some central repository? That's where the edge computing comes in. And if you want to get a job in 2018, you need to know the ABCs, AI, blockchain, and chatbots, right? So that's the Forbes magazine said that, okay? So this is the crowded space of unicorns today, okay? You have started from 2009 to today. All these companies have turned into unicorns, right? How did that happen, right? Why am I emphasizing that? Because around 2014, the cloud became very mature. Your open source technologies became very mature that can be used. And a lot of startups had a short life cycle. They could churn the product very fast because cloud was so mature. Cloud became so mature that you could, so you talk about Heroku, you talk about AWS, Google Cloud Platform, right? All these applications on your phone that synonymous to all these logos here, they are all hosted on a cloud. So today, if I want to make a clone of Facebook, I can do it in 20 minutes. I can go to GitHub, pick up the code, deploy it on my Docker, on the cloud, on AWS or Cloud9, right? And deploy it on Heroku. It's running on an elastic cloud, right? So that's why all these companies became unicorns so fast, is because all these platforms were developed and it got evolved over time, and now it's ready for everybody to use. It's very cheap to do that. You don't need that much money to develop applications and build it and launch it, okay? So these are the acquisitions I was telling you about, all are around AI. Each of them have unique applications, okay? Unique applications for each of these companies. Like Nirvana was bought by Intel. It's the GPU platform, right? Saffron is a development platform, right? Apple bought Turi, it's a development platform, okay? It's like Anaconda or other libraries, but that are focused on AI and machine learning. Then you name it, Moodstock was bought by Google. So you saw Sundar Pichai give a presentation in the keynote, in the I/O conference, where he was talking to the agent, going back and forth. That's Moodstocks, right? The Tuple Jump was bought by Apple in late 2016. That turned into a coding platform, okay? So all these companies have unique capabilities. Now these big ivory towers of technology has bought them and put them in their operating systems, on their devices, or they build the product by itself, okay? So Dr. Jensen, he's the CEO of NVIDIA. He showed this slide in the GTC conference in 2017, March of 2017. And he talked about three things: the big data, the GPUs, and the algorithms that turned into a big bang. Okay, so I took an AI class in 2002 at Cornell University. A lot of scientists from T.J. Watson Center at IBM in upstate New York taught that class. And at the end of the class, they said, okay, don't waste your time on AI. It doesn't work. The error rates are very high. You can be a professor if you want, but if you want to work in industry, these things are not used right now. All right. And most of the funding was done in Canada. US government has stopped funding in AI research. Okay. But then what happened in 2014 around, there was a big bang. Big data was mature, GPUs, technology was ready for AI, and algorithms were ready for AI. So I have a very good friend, he's a general manager at NVIDIA. So I was talking to him because we wanted to build some products together. So he said, like, Jen Sung, the CEO of NVIDIA in 2013, he took them all in the room and he said, okay, we're going to build self-driving car for Elon Musk. And everybody was looking at each other because NVIDIA stock was $2 at that time, right? And everybody was talking about, everybody is looking at each other. I was like, what is this guy talking about, right? He said, oh, I met Elon Musk. We are building, autopilot, and he needs our help. And he's my very good friend, and we are going to build GPUs for self-driving car. And everybody's looking at each other. He said, go do it. That's my order. Just go build it for me, right? I want GPUs designed for Tesla's Model S, okay? And there was no car at that time. Nothing was ready. And the employees were like, okay, we need our jobs. Let's go do it, right? And then after a year, there was an announcement that, okay, NVIDIA GPUs, 7 GPUs are in the Model S, okay? So they said, okay, how are we going to build these tools, right? We need some platform. We need hardware, software for it, and we need to train these algorithms on something. So they went to Belmont, California, Electronic Research Lab, ERL, right? ERL is Volkswagen, owned by Volkswagen, and they also have Lamborghini, Porsche. They have all these different top brands, right? They build electronics and systems for all these cars. They went to Volkswagen. They said, okay, guys, you are building, you have these camera systems. You must be having content to train these systems. Can you share it with us? Then Audi said, okay, we're going to share it with you. So they shared like 500 terabytes of high quality video content run on Autobahn in Germany. And they said, okay, you can take these videos and you tell us what you need, okay? So NVIDIA engineers took those videos, but they run out of it in a few days because you need so much to train these algorithms. So that's the big bang I'm talking about. GPUs, algorithms, and big bang that turned into research in different universities, mainly in Canada. So University of Toronto, University of Montreal, then we have McGill University, right? All the scientists come from there. So Dr. Hinton came from University of Toronto. Dr. Bangio came from University of Montreal. They developed the technology. So we have Berkeley, you have Carnegie Mellon. Berkeley has Café. Carnegie Mellon has MXNet. Then we have NYU has Torch, right? And then University of Montreal came out with Theano. Google came out with TensorFlow, which is essentially University of Toronto's development because Dr. Hinton joined Google, okay? So all these, and Oxford has its own AI platform. So all these were in making since 80s. So we call it AI winter to AI spring to AI summer we are living in today, okay? So these three transitions, so I remember picking up a Discover magazine my father picked up in 1982, and he brought it to home, and I was reading about it. I was just very young, 10-year-old, and he showed me this is the future, this neural network in 1985, okay? But at that time, it was AI winter. Nobody cared about it. There was Dr. Hinton at that time, maybe 30 years old. He was working on it at that time, but then it just disappeared because there was no computing power at that time, right? But it did show some promise at that time. And then the work was going on, and what we're seeing today, the TensorFlow and Theano of today is 40 years of work, okay, 30 years of work, okay? So all these universities have done tremendous research in this area. Then came up core technologies like Facebook got Dr. LeCun from NYU, and they got Torch. Okay. Then Google got TensorFlow from Dr. Hinton, and then now it's a big deal. Microsoft FCNTK, now they call it Brainwave, because Intel bought Altera. Altera is FPGA, right? So FPGA can run very fast AI if it's programmed right, okay? So then Microsoft and Intel came together, they built a Brainwave platform. So if you go on Microsoft Azure, you have instances where you can use FPGA to program, okay? Then Berkeley has Caffe and Caffe 2. These are pre-trained networks, right? And then you have University of Montreal as Tiano, and Dr. Socher developed Chainer. Chainer is from Stanford, and Salesforce works with Dr. Socher in Stanford. He teaches course CS214T on NLP, okay, and recurrent neural network. So now all these technologies were good and the frameworks were good. They were open source. Now they got commoditized by cloud platforms. So now you can buy an instance that is running GPU-based TensorFlow on AWS. So there's an operating system called Bitfusion, which is written, they got funding of $50 million last year to build operating systems, Linux operating systems for GPU-based AI programming. So they built it, and all the instances you all will get at the end of this class today on AWS will have Bitfusion running on it. That's an operating system. So that's AWS commoditizing AI. I'll show you a lot of demos. Then IBM Watson has Bluemix, and Bluemix has the same platform. Google has Google Cloud Platform and machine learning on that, and AI on that. Microsoft Azure has Brainwave. That's a platform. AI is a platform. And then comes all the startups that are bought by technology companies, like API.ai was bought by Google in 2017. Blue River, Clarifai, you have MetaMind was bought by Salesforce. Drive.ai, Nirvana was bought by Intel. All these startups came out by using the cloud and the core technology framework. Now they are doing a lot of interesting work with more than $5 billion in funding in 2017, okay? And then comes industry leaders. They want to change the world. As a lot of students said, that's the future. So if you go back to digital evolution, right? 1950s first electronic computer, to today, with all these multi-billion dollars, hundreds of billion-dollar companies, with the cloud impact, right? How cloud impacted the industry today. So now you have everything on your fingertips. You can start a 4K video on your phone, if your phone supports that, just by pressing few clicks, right? Uber has its own, right? It's a sharing economy. Spotify, Airbnb, Pinterest, WhatsApp, Uber, HelloFresh, you name it. These are all multi-billion-dollar companies, but were created with cloud impact. So, but we are living in this digital correlation today. The cloud has reached its peak, okay? So the cloud is not able to serve the AI economy of today, right? So cloud computing, artificial intelligence, data analytics, Internet of Things, and fog computing. And all running on a blockchain. That's a digital correlation we are running today. And cloud is not able to support that. So that's why we are talking about fog computing, right? That's edge computing. Quantum is maybe 10 years, right? But this is here today, okay? Because privacy is a concern. Nobody wants to share their information on the cloud because it's being misused, right? To influence social science these days, right? We see what's happening in various countries in the world. So with fog computing, your analytics will be sitting on your device and not on the cloud. So nobody can share it. It's your own. You want to share it, you can share it. Or you get monetized for that, right? If you have somebody who want to use your data, you need to get paid for that. So that's the fog computing and Internet of Things. So that's the digital correlation we are living in today. So Dr. O'Reilly, Tim O'Reilly, he runs O'Reilly Conference, and he has a lot of good books, with all the different crazy animals on it, right? O'Reilly publication are my favorite. So that's because the primordial soup of AI, right? AI really jumped into mainstream because of big data infrastructure, cloud computing, massive amount of data, Watson and CD, venture funding, and qualified people. all these coming together, build that, okay? So then a lot of countries are investing a lot of money and a lot of good applications of that. So you see NVIDIA stock went up 1,200% in last year, right? I bought it, my friend told me when it was $32. So he had just sold all his stocks and bought a home in Los Gatos. He said, I made a mistake. Please buy it if you want. Whatever money you have, buy the stock. I did not put a lot of money, but I did put some. But I sold it at this point. I never thought it's going to go up again. But then it went up, you know.
What happened to AI? AI should be predicting that.
Exactly, right? So Dr. Jensen Huang was named Business Person of the Year by Fortune magazine. And exploding demand for NVIDIA's advanced chip inside everything from video game systems to AI-powered cars has boosted the company's market value to some $130 billion, okay? So you have NVIDIA, you have AMD, you have Intel, all of their stock going up because of the demand in the GPUs. So no company wants to be called a chip company in Silicon Valley. Everybody wants to call themselves as a data company or a platform company, right? So no one in Silicon Valley wants to be called chip company these days. Yeah. Qualcomm, which makes processor found in many Android phones and iPhone modems, describe itself as a platform company. Yeah. Intel, once proudly inside most of the world's PCs, now position itself as a data company.
Yeah. And you mentioned Altera with FPGAs.
Yeah. Yeah. NVIDIA, whose soaring share price has made it one of the best performing stocks of any sector in past 2 years, describe its graphical processors amplifying human intelligence, okay? So these are the 4 big chip companies, Intel, Broadcom, Qualcomm, and NVIDIA. It's betting on a big bang of AI, right? So Broadcom bought Computer Associates yesterday or day before. They have been acquiring company like I think
they bought Brocade.
Yeah, they bought Brocade, and Cavium was bought by Cavium was bought by NVIDIA, I think, just 3 days back. So a lot of acquisitions happening in the chip industry, and Apple has a big gauntlet with Qualcomm, and that's going to be settled outside the court, maybe. I don't know, because both have enough material. Yeah. Right. But then you need hardware to run these things, right? So there's a space for that.
Yeah. What about AMD? Like I see it outperformed in Intel. Why is that?
But AMD is so they are making customized hardware for cryptocurrency mining, the GPUs, and because there's demand for NVIDIA GPUs, there's demand for AMD GPUs also has gone up. So maybe they are doing some customized solutions for few of the companies who are not with NVIDIA, right? So they have won some contracts too, right? Because it's just a market. They are good at GPUs also. So Bitfusion is what we are going to use in this class. Bitfusion raises $5 million for its AI lifecycle management platform. So if you go to AWS and look for Bitfusion, you will see they have customized operating systems optimized to run AI algorithms, right? So that's that's a big deal. So there are a lot of news items. I'm not going to go through all of them, but a few of them are very important. Like I was telling a gentleman about Nirvana neural network processors. It's FPGA based, and now they are partnering with Microsoft to build Brainwave platform. And there's this whole new area of chip. I worked with this person, Excel Cloth. They're making a lot of the brain-like computing with new self-learning chip. So Intel has built Lohi, is their name of that. Apple has Bionic chip on their phones for doing the face recognition. And there are a lot of other chip platforms. They are being built to work like a brain, right? So they are good at doing neural network operations.
Yeah, TensorFlow now is doing some development where they're going to actually be doing JavaScript coding from TensorFlow.
Sure. Yeah, that's in making for a while. Yeah. So there's a lot of these computing is moving towards brain-like operations, because if you know it, like the CEO of NVIDIA says it very well. He says, okay, what's the difference between GPUs and CPUs? CPUs are good at doing logical operations. GPUs are good at doing matrix operations or solving differential equations or doing some calculations like a brute force. Like we play video games, you see repetitive patterns coming in again and again. You see like landscape being made or explosions and stuff like that. So those are repetitive stuff, incrementally changing over time. So GPUs are good at doing that. So he explains it in a very layman terms. He said, like, you want to deliver 10 pizzas, okay? Either you drive a Ferrari to deliver it or you drive a moped to deliver it. So the GPUs are like mopeds. So you can buy 20 mopeds and deliver the pizza, or have a Ferrari deliver 10 pizza one at a time, right? That's a CPU, right? So he compares the
teacher cost.
Yeah, exactly, right. So he compares the two, and it's coming. We'll talk more about it. So this TensorFlow lattice is come out last year, which makes the machine learning models follow global trends. So I was telling some students who came earlier today to talk about, like, okay, you build the machine learning models, but how do you know if it's good, right? So what does TensorFlow lattice do? It compares your result with global trends and tells you if your model makes sense with global trends, okay? So there are quite a few applications, like self-driving car is taking up. So nowadays, I'm teaching a course on self-driving car. So there are a lot of open source packages now that can let you make applications of self-driving cars. That's a big deal. So a lot of activity happening in this area. This is Dr. Hinton. Yeah, it's Jeffrey Hinton. He is the father of AI. Okay, so he was addressing ARIX conference last year, and he said that back propagation doesn't work. We need to redesign it. Okay, that's when capsule network came out. So this is a capsule network. We'll talk more about it later on. But this capsule network not just do feature engineering, but also does classification. So what he says that he's a neuroscientist. So he thinks like a brain, okay? So how does brain work? And his work has been that, okay, we do this forward prop, backward prop, but our brain is not just doing forward prop, backward prop, but it's using the previous memory that you have, events you have gone through in your life, and also doing classification at the same time. So he added the classification at the end of forward prop, and then using that to make sure that it doesn't do this type of stuff. So AI is like a brain. It's like a small child, a 2-year-old child, okay? So a 2-year-old child gets attracted to colorful things first. So this algorithm is here to classify banana photos. So it's supposed to go and say, okay, this is a banana. But if you put the psychedelic image next to it, it will detect that first.
It's distracted.
Yes, it's distracted, right? So capsule networks help you remove that distraction. So a lot of cheating happening, like this guy has wearing this glasses. So your face recognition won't be able to detect his face because he's wearing a glasses with this print. The AI is going to detect the snake that's printed on the glass, then the face, okay? So capsule networks help you defer that, okay? Same thing with the tortoise. You have the 3D printed tortoise, and there's a pistol printed on the top. It detects the piston first, okay? So that's the capsule network. So you can go through this on your own. There's quite a few interesting stuff that's happening in this area. If you have any questions, I can answer that for you. So these are all the news items that have happened in last year or so, because AI is becoming a big hype. Okay, so that's why. So this is the hype cycle from Gartner last year. So what you see in innovation triggers, and then you have peak of inflated expectation. All these technologies you see on the left are all AI powered, most of them, or they are complementing AI. So if you focus on these technologies today, your 10 years are going to go very well, because all those things will become part of your job in 5 years. That's what happened in big data. It's happened in machine learning, AR, VR, you name it, blockchain. They all became part of my job in 5 years. I started learning it 5 years back. Now I'm using Hadoop as a daily job, right? So all those things, it's very important for you so that you are at the right place. You're focusing on the right thing for next 5 years, right? So what are the market drivers in AI today? GPUs, FPGAs, ASSPs, increase in data. You know, the data is omnipresent. Even when I walked into the store, Facebook said, okay, you're visiting CSTU, can you review it? Do you have opinions about? So they are following you every time. So you go to your, if you have an iPhone or an Android phone, you can go to your, go to privacy and go to analytics and go to analytics data. These are all the logs being created as I was driving from my home to here. All these logs are being created. These are all JSON files of like different stores who are eavesdropping on me, or some apps were taking my lat long. So you see all these logs being created as I was driving, and I have the same phone as you. People like that. I have applications here. They were tracking my location, or they were watching what I was doing on my Facebook while I walked in here, or what mapping app I used, or these are all the logs being created. So no, this doesn't get shared. This is on my phone, but some of them does get shared because I have opted in to share my data to improve. So this is another application that's tracking everything. All of your phone have it. It's not just my phone. So all these things are logs created. So that's a lot of data, increasing data. My phone has maybe 250 gigabytes. So 30% of it is logs, because I need the logs to run my applications, right? All of your phone needs logs because that tracks your usage, right? So all that increase in data, just smartphones, right? Smartphone is kind of part of your body now. You can't run without it, right? Hardware performance, GPUs, FPGAs, because all these technologies, AI technologies, are brute force. There is no science as such. You're just fitting models, but at a scale that never seen before, right? Software algorithms advancing. So what was happening when I took my first class in 2002 in AI, they call it neural networks at that time, was the error rates were more than 50%. That's worse than a coin toss. A coin toss is 50-50. So error rates were 60-70%. That shows that it doesn't work. Why it was not working at that time? Because because we were always overfitting the data on training data. Okay? We were overfitting most of the time. So when you do overfitting, the training data works very well, but when you put new original data, it always goes crazy error rates. So software algorithms advanced to mitigate that. So we have regularization methods that mitigates that. Macro markets, economic trends. Now that our smartphones are personal devices, our cars is our personal device, right? Our home, when you walk into the home, it's your personal place. All that environment has been exposed now, right? Because we have our home, Google Home or Alexa in our home. We have our televisions, we have our phones, we have our car, or your workplace. Every time you are interacting with the cloud or interacting with your device, or you're speaking, you're watching TV, all that data is being created, and that's attached to somebody living, right? Market barriers are technology limitations. As I said, cloud has reached its maturity, right? Gap between expectation and reality. So we are saying that, okay, AI is going to solve all the problems. That's not true, right? So self-driving car is great, but when will we have it? We don't know, right? Maybe next year, 5 years from today, maybe part of it, maybe 30% of driving will be done by self-driving car, or some of the cars will be self-driving, like buses who have predictable routes, or trucks, or some other transportation. But yeah, that's so we'll talk about that. I have a chapter on that. They are level 5 or level 4 but to get to level 1 is tricky, right? So we'll talk about that. So political regulatory factors, shortage of talent. That's why we all are here learning, so that there's enough talent out there, right? So Dr. Thrun, he runs Udacity.com, right? Udacity is big training. He claims that $650 billion will be spent in AI in next 5 years, right? Immaturity of the market, right? Market is not ready for AI, right? So all those are market barriers, and all these things are going to happen, okay? So this is the technology stack of AI. I always focus on this side of the technology stack. So if you want to learn AI today, okay, you need to know research. I've been talking about a lot of history behind AI today. You need to know the research. What research is going on? OpenAI, Element, Vicarious, Numenta, Cogital, right? Hardware. We talk about a lot of our hardware. A lot of people here are hardware engineers. Hardware is very important. It's a basic building block of technology stack of AI. You have NVIDIA, Nirvana, Movidius, Tensilica, Google TPU, TensorFlow processing unit. That's programming JavaScript that he was talking about. 1026 Labs, Qualcomm, CIMAScale, TenStorrent, Canupath, right? These are all these hardware. Open source libraries like Keras, Chainer, CNTK, TensorFlow, Caffe, H2O, Deep Learning 4J, Piano, Torch, Scikit-learn, Azure ML, Neon, MXNet, DMTK, Spark, Paddle, Weka. All these are open source libraries. Then you have data capture. How do you capture data? So now you must have heard about Figure 8. It used to be called Crowdflower before. This is crowdsourced data. Like you want to know, you want people to just look at the image and say what it is. So there are like these mechanical Turks around the world who are given like 5 cents per image. And they look at the photo and they say, this is a dog. Because you want to build the ground truth, the content creation, right? There's Crowdflower, Discord, Crowd AI. These are all data capture. Trifacta and Google Cloud has tools to use machine learning to do big data. So let's say you load log files like I showed you. Let's say today Google is hiring people good with JavaScript and AngularJS to sift through almost 75 petabyte of Pixel 2 logs. Yeah, somebody can look at that, right? Right now it's sitting in some data center in Oregon. Nobody's looking at it. All these logs of people using Pixel 2 phones, right? They want to parse it, right, and see what's going on. So they're using Trifacta to do that. So Trifacta makes your life very easy. Okay, we'll talk about that more. Then you have development tools like Rainforest. Bonsai was bought by Microsoft last month, right? Bonsai is an AI platform for gaming. Anodot is a very big company. Anodot is for in development side of things. They have platforms built, a cloud engine built to run AI on the cloud, right? Using Elasticsearch, using Hadoop, using Spark, using all these different libraries. They've built stack that can run AI. Natural language processing, very important. We'll be doing it in 5th week. NLP for chatbots, conversational agents. How do you make sense of? There was a lady who talked about conversational stuff that she has worked on. So natural language is very important. Machine learning is important, right? All these tools for machine learning. Data science, right? So that's the building block. And then agent enablers on the top, like Maluba or Kit.ai. These are all bot platforms that are needed. Okay, there's a technology stack. And then AI is, we are using all these tools in AI to for building in different areas of enterprise. All these companies who are supporting AI. Okay, so these are the companies who will hire you. A lot of opportunities, and many of them are in Bay Area. Okay, so then this is where the focus is these days. Okay, your natural language understanding, 505 companies doing that. Deep learning for image processing, 197 companies. Cognitive computing, right? Then autonomous vehicles and chatbots. These are the areas where most of the investment is being made in AI today. Okay, And most of the companies are doing lab projects today. So I was talking to Jet Black. Jet Black is Walmart's Amazon arm. Like they're trying to emulate Amazon. So they bought Jet.com 2 years back. Now they have Jet Black, mainly based in New York City area. They are building agents for mothers. They are building agents for 15-year-old, a 12-year-old, how they will talk to them to sell stuff. Because the conversational AI is at a level today where you're going to have a continuous conversation with the robot. And still the robot will understand what you're talking about, right? And not forget what you said 15 minutes back, because it's tracking what you said. So Jet Black, I was talking to a recruiter from there, and he was saying that, we are building these agents, and we need research scientists who can create content and train these models, because we have the algorithm running now. It works, the conversation, but now how can we build content for mothers, for 15-year-old, a 12-year-old, a 10-year-old, right? So that's the lab projects. And the salary they were offering me was just unheard of. I couldn't believe what he was telling me about. I was like, are you sure you're talking about this much salary? He said, yeah, if you qualify, we'll pay you that kind of money, because there's so much demand for this. Like they're building lab projects to demonstrate these things, okay? Building applications and strategic direction for business, okay? So let's get into theory now, okay? So how do we define intelligent systems? How do we define intelligent systems, okay? There's machine learning, there's data sources. These two things don't change. But how do we build intelligent systems is, first you need to communicate information with humans, answer queries and infer new facts, and to store complex information. So these two things are going to complement enablement of these three, okay? You need data sources, petabytes of data, you need zettabytes of data you need on the data sources side. You need advanced machine learning algorithms, okay? To do these three things, natural language processing, okay? Because if you can't communicate information with humans, humans are right now superior than AI today, okay? We don't know the future. But today they are more sophisticated, and humans want to use AI to facilitate day-to-day things they do so that they can do something better, right? So how do you communicate information with humans? Only way you can do it is using natural language processing. So you use a bag of words, you use spoken part of speech, you use all the different tools that are in NLP, like word embedding, you use all these tools that are part of natural language processing toolkit. Like you have Stanford and NLTK, we have Spacey, we have Microsoft has its own NLP library. Microsoft is the most advanced in NLP. They bought Maluba, they bought Bonsai, they bought all these companies. They are very good at natural language processing. We'll be talking about that in 5th week. Automated reasoning, answering queries, infer new facts. Knowledge representation, to store complex information. How do we do that, right? So all these things, you need a tremendous amount of computing power to do that, right? And we will, at the end of this course, we will definitely know how to get data. We will know machine learning, and we will know how to do these three things, right? That's the goal of this class. So how
exabytes of data?
Yeah, pretty much, right? My manager asked me, like, okay, we are going to get all these logs from the phones. Like, there's more than 1.3 billion iPhones out there. All these phones sending battery usage data. How are we going to store it? So we said, okay, use the cloud. So we tried cloud. The latency was so bad, we couldn't run our algorithms on it. So eventually, we went and got these G-RAID drives of a terabyte under my desk. So now I have a terabyte, maybe around 75 G-RAID drives sitting under my desk, because I can't deal with latency when I'm doing research projects, right? So a terabyte sitting under the desk, I couldn't imagine that like a few years back, right? So AI, these are the projects we are going to work on, right? Reasoning, the ability to solve problems through logical deductions. Knowledge, the ability to represent knowledge about the world Planning is the ability to set and achieve goals. Communication is the ability to understand written and spoken language. And perception is the ability to deduce things about the world from visual images, sounds, and sensory inputs. These are the domain problems that AI is solving today. Domain expert, they want to become a domain expert. So like creating fake news, right? You have to become a domain expert to create fake news, right? AI is creating fake news, problem which involve reasoning based on complex body of knowledge, okay? Domain extension, problem which involve extending a complex body of knowledge. For example, let's say you build a bot that will help you shop, right? That's an extension of your domain, because your domain knowledge may be how you design the dresses, but then how will the AI robot can extend that and help you shop. Complex planner, so you can do tasks which involve planning. Okay, so you put in all your calendar for last 10 years. If you're doing the same job for 10 years, you can put all your calendar information. Then the bot will know what meetings you will need tomorrow, right? If you're doing the same job. Better communicator, tasks will involve improving existing communication. Can you write memos and letters for you? Like Siri can do that, right? You can say, okay, send this message to my assistant. It will write it for you. Maybe you can just say it in some language, it will translate and write it for you, right? Better communicator, new perception, tasks will involve perception. Enterprise AI means re-engineering the corporation. Problem which impact domains due to second order consequence of AI. So for example, AI will put a lot of people out of job. Then how it's gonna work, right? That's a problem too, right? Problem in near future. Exactly, that's the problem, right? The problem in near future that could benefit from improved algorithm, evaluation of expert systems, super long sequence pattern recognition. That's the agent I was telling you about. You can have a 15-minute conversation. I've been talking for last 45 minutes. So all that conversation I talked about, can an agent listen to me and say what I was talking about? Or maybe compress that and say it in few words, right? That's a super long, or maybe put all of the S&P 500 index data for all the transactions ever done, right? And put it to the AI, and will it tell me what will be the price of a given stock? Right? A super long sequence. Like currently they use a time series, high frequency trading, but this is out of this world, what it can do, right? Super long sequence. So some of the demos we will do at this week 7 and 8 is face generation. So you put in all our faces, and can it create a face based on all the people in this room? Face generation, right? Can it write by itself? After you give 50 books, the AI will read 50 books, and then it will write its own sentences based on that, right? Text generation, right? Can it change the outside is summertime, summer afternoon in Bay Area? Can I change it to winter? Same area, right? Just change I just change the temperature. Okay, right now it's 80 degrees. I change it to -5 Fahrenheit. Can it show what it will be if it's -5 Fahrenheit? Just train models, right? That's the just generalized additive models, right? Or adversarial models. Or can I give a game for the AI to play? And nowadays, it used to be, moonshot, but now it's available. You can run it on your computer, right? Existing sentiment analysis. So I'm taking somebody's interview, and just by looking at their body language, I can say a lot more than what that person is saying. So can I record that interview, and at the end of it, it will tell me what this person's intentions are. So we do that at Apple, not at the AI level, but when a customer walks in the store, as soon as they set up the concierge appointment, they put their phone serial number, okay? So we will know everything about that person, not personal information, but how many SIM cards that person changed, how many phone numbers this changed, how many countries that phone has traveled, how many networks it has interacted with, what were the IP addresses, what were the MAC addresses, what all Wi-Fi accounts it went through. So that way we can clearly say this guy is a fraud. This person is a fraud, because if this phone has gone through 15 SIM cards, it has been jailbroken many times, then we will give them a red color. if this customer has 25 Apple devices and he has been a loyal Apple customer for the last 10 years, we will paint him green because that's a VIP customer for us. We will treat them with the first class. If there is something in between, we'll paint them yellow. Then they put to a slow lane. They're put into a slow lane, right? So we do that currently. Like yesterday, Walmart filed a patent for eavesdropping on the employees and customers. So as soon as they walk in, they're going to put cameras and speakers inside Walmart. So when you're talking, it will know what this customer's intentions are, right? It's a patent has been filed. Amazon has a store now that you can walk in without any agents. You can purchase and walk out. You don't have to scan anything, and it will charge your credit card for that, right? So all these things are extension of sentiment analysis, okay? So this is AI revenue over next 10 years, and the amount of data has been growing, right? And most of it is unstructured. Like I was telling you yesterday, voice, right, is unstructured. There's no way you can structure it. Log files, lat-long information, people interacting with the systems, or your phone, or your Google Home device, all that information, unstructured data, right? Self-driving car, it's taking videos. So self-driving car, like in Facebook F8 conference last year, the CTO of Facebook said that our eyes see 4 terabytes a second. What our eyes can see today, high-def content, 4 terabytes a second, right? So can we use that to predict, or can we use that to recognize objects, right? Because cameras are as good as our eyes nowadays, right? So our car, when you're driving a car, if you put 7 cameras, right? Tesla has 7 cameras. Some are high def, some are low def cameras, but they're all around your car, and front, back, sides, right? But if you look at it from a human perspective, when you're driving, only 5% of time, less than 5% of time, you're looking around. Most of the time you're sitting. So they put high def cameras in the front because that's what driving is going to be. So that's like 17 terabytes a minute, right? That's the content being generated. That's why they need 7 GPUs inside Tesla to process all that information for autopilot, right? And still they fail. Still they're not able to. So the car that, the fatal accident on Mountain View 101 was, the car hit a point that's a small, like 7 millimeters. That's not covered by the camera. It hit there. And that's when it turned into fire, because that part was not covered in the camera. Rest were covered. So that's the unstructured data we are talking about, okay? And so let's get into the meat of things, right? So traditional programming is data programs and computer and output. So let's say you write a SQL query on a database. You are writing a SQL query. The data is coming from the database. You're putting it to a computer, and it gives you the report on the other side. Machine learning, you give data and output. This slide is from Dr. Ng from Stanford. He teaches Machine Learning 101 at Stanford. So you put data and output, and program comes out the other end. Okay? So that's the machine learning.
Where's the output?
Yes. So output is either it's a fit. You're running a machine learning model, right? So you have ground truth.
I know. You say the output is the output comes from the traditional programming.
No. They're two different things. This is the definition of traditional programming. This is machine learning. So how is it different from traditional programming?
Data, program and output.
Yes. So you give data. You give data, that's a production data or training test validation data. And then you give weights and model, right? And then you need to give ground truth, right? Ground truth. And then it'll give you a program on the other end. So that you can use to test or run your production data, right? So this is an engine. So like I just told you about Apple, when you walk into the Apple retail store, as soon as you book a concierge appointment, we look at all that information. That's the output. That's output, right? You're putting that to the program. like how many SIM cards you changed, how many countries you went to, how many phone numbers were changed, like that. We have around 15,000 parameters like that, right? So, and we keep improving it as we find more modus operandi of the fraud people. We update it every day. We have new features added.
They really do that, because last time I was in Apple Store, they commented, "You travel a lot."
No way, really? They should not be doing that. They shouldn't be doing that.
Before we say
Wow.
before the traditional computer, we say garbage in,
Very
garbage
dangerous.
out. But
Right
how
now
about
it's
the
everything.
machine learning? You have output. Those output in, about the output, you need values.
Yes.
output,
So that's the key about any AI, right? You need your output. Output needs to be. That's why we call it ground truth, because you need to have a good confidence on your output. Yeah. That's why the content. That's what I started with, right? The content creation. Content creation is output. That's your key in building your model. Okay. So that's the data and output, okay? So your problem definition, data generation, raw data, pre-processing, pre-processed data, machine learning, hypothesis, validation, knowledge and predictive model, okay? So now, when you talk about problem definition, that's your business problem, right? So when I started working in battery engineering, that's a $5 billion problem for Apple today, is because customers are returning phones, and they're not happy with the battery performance. And we acquired a company in hometown of Dr. Quinn in upstate Fujian province, and the place is called Nigde, right? So that plant is making almost all the batteries for Apple iPhones, and also for other, like your hoverboard and the Bird scooter, and you name it. All batteries are made there. It's a strategic location for Chinese government. And so when we bought that company, before that, there was a lot of issues happening with the material, because the material comes from Africa, some like cobalt, lithium, very endangered material. So Apple doesn't believe in non-fair trade. They buy the mines itself. They make sure that it's fair trade. And they bring the material out to the factory, then they fabricate it. So the problem we were having is we wanted to identify why the batteries are draining so fast, right? There are many, many factors in the factory, in the assembly factory at Foxconn, or is it the customers using the phone? What apps are being used? Is the app design is wrong? Like Facebook is not designing apps properly; they are just leaking power. Or Snapchat or this Uber application always eavesdropping, because when you start Uber app, as soon as you start the Uber app, how does it get all this information? Because it's running in the background all the time. Whenever you drive around, walk around, the Uber app is always taking a lat long. So when you start it, it's ready. It's showing the information. So this was the problem definition, that we want to know how the battery is performing every second. So we set up problem definition. We went to our senior VP. We went to Tim Cook. We said, okay, guys, we have a big problem with batteries, right? Customers are setting it up in the house and saying that the new battery is better than old battery, and throttling and all those issues happening with the battery. So how do we improve the battery performance? That was the problem definition. So now then we went through data generation, raw data, pre-processing, all these information, all these steps took around 7 months, almost a year. And then we came here to machine learning. Then we went out to buy the consultant who can do the machine learning for us, because this was at petabyte scale. I can't do it in my lab. So we went out, we went to the big guys like IBM, Accenture, Booz Allen Hamilton, the big names. None of them could do it. None of them, like IBM brought in Watson, then we had Accenture come with their own best of the best tools. We had other leading companies come, and SAS and others, but nobody could solve the problem. And then we had to build something hybrid, that would work out real-time machine learning. That took another year, going through the vendors, then hypothesis, validation, knowledge predictive models. Now, if you have an iPhone, you go to your privacy, you will see a battery health check application.
Yes.
We built that, right? That's in beta today. But what we are building here is predictive model that could tell you that your battery is going to fail in next 30 days. Go and replace it. It's in warranty, right? So that's the model we are building. So this took 2 years to build. Machine learning has a problem. Machine learning has a problem because, first of all, the biggest problem is feature engineering. You have to engineer the features, and engineering the features, if the problem changes tomorrow. So let's say the vendor we are using today doesn't work. We go to LG, we go to Samsung, we go to Sony. We are going to have different problems with them. They have different architectures of the battery. All of this has to be done again. We can't use what we have learned here. And that's the problem with machine learning. That's where deep learning comes in. AI is a brute force machine. So you don't have to do feature engineering. It's a black box, right? You apply a black box. It's a brute force machine. So let's say I have a Rubik's Cube, okay? Rubik's Cube. I want to get the 10 on 10 on Rubik's Cube, right? All the colors are right. I can design a robot that would do it for me, right? I can design a robot, move it, all possible combinations, right? And eventually you will reach the solution. It may require maybe a day or 2 days, 3 days. There are robots like that out there, okay? That's called brute force. It's trying all combinations, right? Deep learning is essentially a robot, a brute force robot. It's trying all combinations possible. So let's say I have a mannequin. I want to fit a model on the mannequin, okay? So I can put some complex surface on it. Now I have to try different ways how it can fit the mannequin right, okay? That's what deep learning is all about. It's brute force machine. That's why you need GPUs, right? GPUs, FPGAs, right? So it can do brute force. Try all different fittings, right?
Cryptography.
Yeah,
right?
exactly, right. Before the quantum computing, right? But today, you need to try all different ways you can fit. And then you're going to run it multiple times, hundreds of thousands of times. You're going to run it so that it fits perfectly, right? And then you want to make sure it doesn't overfit. So that's why you do regularization. You drop some signals and you fit it again, like a bagging, you know? You have a bag of balls. You take some balls out, you see the color, put it back, take them out again, and then calculate the probability. Same way, the deep learning is a brute force machine. So you're not doing all these steps. You're skipping all the steps, and you're applying this robot that will brute force find a solution for you, right? Because it has tried all different possibilities, the answer is better than this way, okay? So that's what we're gonna learn here. So how many of you have taken machine learning class? 1, 2, 3, 4, 5, 6. Okay, all right. So you must have learned these techniques in machine learning. Okay, it's not required to know machine learning. I will go through that, but these are some of the methods. So I was at recently. I was at Uber. Okay, Uber. There was some consulting project. We were trying to solve some delivery problem. Uber Eats. Okay, very complex problem. So the consultant, we asked this question to the problem, right? We have all these different classification problems, blue and red dots. I want to classify the two. Most of our life problems are classification problems, okay? Anything you make decisions, right? Yes or no, right? Ham or spam, right? All of them are classification problems, right? Either you apply a regression tree or a classification tree, a binary tree, but you want to classify, okay? How do you classify? The first is brute force based nearest neighbor, okay? Nearest neighbor, I look at my neighbors, are they the fraud or not? I just look at, then I go to the next house and look at my neighbors again. It's very brute force based, right? Then you see the problem space is also like that. Very, very complex. None of the surfaces are the same. Then I go to support vector machines. It's more kernel based, compute intensive method. And support vector machines, I have striations, right? That's how I classify. Then I have decision tree, which is greedy. information gains-based, entropy-based decision trees. The decision trees are rectangular because I'm always looking at levels, factored in levels that I'm seeing. And then naive Bayes is pure probability, Bayes theorem, right? This given this, divide by this given this, I'm getting a Bayes theorem, right? So that's the probability, always circular contours. So these are different ways you can classify machine learning using machine learning. And what I'm able to do tomorrow, once I classify, how does this help me do my job better, right? So I was at Amazon 10 years back or 11 years back. The biggest problem they had was 11 years back when Amazon stock was $30, right? It's a much smaller company. So the guy asked, it was a warehouse statistician position. And they said, okay, we have the biggest problem is 30% of our products are going to the wrong address. And 5% have empty boxes, right? At that time. So how would you solve that problem? As a statistician, how would you solve that problem? So it was a classification problem we were trying to solve. So maybe take an X-ray photo, or you take a weight of the item and to the fifth decimal point, and you'll be able to see that. Or when brute force put a fan, so empty boxes will fall, right? So all these ideas I gave at that time, but the solution was classification, okay? So any problem can be solved with these, but there are all these different methods. And you see the accuracy. For every problem, the accuracy of one of the model is better. Like in linear SPM is worse for this circular classification problem. You can't do that because the problem space is always straight. You can't solve a circular problem. Versus in this case, you have decision tree is worse. In this case, naive Bayes is worse, and SPM is better here, right? So how would you solve this type of problem? Because you have all these different problems need different feature engineering, right? How would you solve that problem? That's why you need deep learning, right? So this was from PwC's strategic document they published last year, where they talk about five tribes of machine learning scientists, okay? So when I went to graduate school at Cornell University, we had a department of mathematics, Mallet Hall. One side was Bayesian statisticians, other side of sampling statisticians. They don't talk to each other, right? They're like, okay, we win and you win. At that time, nobody knew, right? Sampling guys said, we're gonna win. Sampling statistician are gonna win. Bayesian, like probability is going to win. But sampling statistician were winning because there was no computing power. We had gold-plated hardware. You know, memory industry was going through price fixing problems where Elpida, Micron, Samsung, Infineon, all these companies were sitting in a table and said, okay, you make this much and you charge this much. Price fixing. Then Elliot Spitzer, he was the Attorney General of New York, you know, he said, okay, this is a price fixing going on. So he just filed a lawsuit and he shut it down. Now then the memory prices dropped. It used to be $1 per megabyte. Now it's it's like few cents per megabyte, right? A fraction of a cent per megabyte. So that's when memory industry collapsed, and that's when everything moved from symbolics to Bayesians. Because it's easy to analyze population, you don't need samples anymore, okay? So that's moved from rules and decision trees to naive Bayes and Markov chains. Yes, Bayesian is probability, right? You must have heard about random walks, like Brownian motions, right? Those are all Bayesians, more Markov processes, okay? So naive Bayes is a Bayesian, okay? Then comes connectionists. So all the millennials I teach these days, they're all talking about connections. They don't talk about Bayesians anymore because everything became brute force, neural networks, right? Cell bodies, synapse, like brain, recognize and generalize patterns. Then comes evolutionaries. When you assemble all these methods together, you build genetic programs, right? And then analogizers, support vectors. Like there was another building called operations research. They were all mathematical programmers. They were talking about optimization. That's support vectors, okay?
Stochastic process.
Yes, there you go. So that's a support vectors, okay? So these are the 5 tribes of machine learning today, okay? So either you start with, if you take machine learning 101 at Stanford, they will teach you decision trees, right? That's the first thing you learn, right? Then you learn, if you are lucky, they will teach you naive Bayes, and neural network comes in the next, like CS 221P is the first neural network course at Stanford. And then you have genetic programs and support vectors. And then 1980s, everything was symbolist, okay? Everybody was talking about ERP systems and SAP and knowledge engineering and quality assurance and all those things in 1980s, decision support systems. Everybody was working maybe a mainframe, right? Computers at that time. In 1990s to 2000s was Bayesian's time, okay? Probability theory, small server clusters. So a classroom where we used to teach, we used to have a room where all the servers used to sit, and we would use that to run our programs. The scalable comparison, contrast, and then connectionist came through. It's cloud. That's what we are going to use in this class. Large server farms and GPU-based clusters, and that's a connectionist, mid-2010s. And then late 2010s is connectionist plus symbolist. That's the capsule network I showed you, where you're combining the feature engineering through neural networks with classification combined together, right? That's connectionist with symbolist. So connectionist with symbolist, you're doing neural networks and classification together, decision trees. And then 2020 plus, you combine all of them, and that's where fog computing comes in. That's your device. And then 2040 plus is server ubiquity, right? Best of breed, meta learning, act or answer based on knowledge or experience gained through various kinds of learning. That's algorithmic convergence, 2040s, okay?
Which company is doing that?
2040s?
Yeah.
That's 20 years from today.
Nobody doing that.
I mean, maybe there's research going on in the university.
Yeah, universities, Microsoft is doing stuff.
Yeah, so there are research projects.
Probably Google.
Yeah. Mm-hmm. Maybe Google or Amazon.
Because
Yeah.
Yes, yes.
You just mentioned 20 years ago that it's only $2. Yeah, they already start doing the graphics card, the GPU.
Yes. No, not 20 years back, but 10 years back. Yeah.
Yeah, but I want to know which company they have mentioned when they start to do that.
I mean, there are projects, right? But then the key is execution, how they can execute it. So the computers to do this stuff is not even built yet.
She wants to buy the stock. So she can get a lot of money.
Maybe Amazon. Amazon is
The basic answer is those companies haven't been built yet. Those companies don't exist yet.
Yeah,
Oh,
not yet.
okay.
yeah.
Choose the best candidate.
That's
Like
one.
Google or Amazon. Choose those two companies. There you buy it. Just go move forward.
Yeah.
Remember when you were
Best
talking
price
in
for the future.
1982 about reading the,
Yeah.
I was talking to a friend of mine about developing language.
At that
you
time.
could do some programming and everything. His name was Jim Gosling.
Wow. You were talking to Jim Gosling.
Oh yeah, Jim's an old friend. Jim Gosling is the gentleman who developed Java.
Yeah.
Oh,
So Java didn't exist then. The company didn't and not
Right.
purchased yet. But Jim and I were talking about that with Jim Gray because I was at Tandem then
Sure. Yeah.
before Jim
Wow.
Gray went to Microsoft.
You
Yes.
see, the NVIDIA 20 years ago, they already started GPU and hold the graphics card because he realized that.
So you should read about Jensen Huang. He was an orphan in Iowa at that time. Maybe 30 years back. I mean, he had a
Most of those
he had a
companies
story.
that you showed on the chart didn't exist
Exactly.
5 years ago.
Yes, that's true. At a level they are today.
Yeah.
Right. So
Should we have some break before?
Yeah.
Just
Can
kind
we
of
have
off
a
on-
break?
yeah, let's take a break.
Yeah.
Okay.
See, whenever he stands up, that's time to take a break.
Okay, cool. Yeah, that's not a problem. We can take a break. So I'm used to teaching 9 hours at stretch.
Oh
So,
my god.
so I mean, you have to tell me.
Like,
Sure.
yeah, usually we get break once in 1 hour.
Oh, that's good to
Maybe
know.
5 minutes, 10 minutes like that. You can tell us. So 10
Okay.
minutes break like
Yeah,
that.
yeah, sure. So usually what I do once we start hands-on, then you will do the coding. So 10 minutes, you will do the hands-on work.
Okay.
So this is just lecturing.
Okay.
So today we finish at 7:30.
Yeah, I mean that's the plan.
Oh, that's the plan. Okay.
That's the plan.
So what's the time for ending?
That's my
Well, it's
personal,
supposed to be.
but
he
this
thinks
is that startup
he thinks
I'm
it's
working with
7:30.
now too. I was a CIO
argue with
100
the
award
instructor.
winner for enterprise application integration. So you can find me on LinkedIn. Send me an invitation. But since I'm at their max for first level, I have 30,000. So if you send me an invitation, well, that's first level, and then I have about 60,000 followers. So, but if you send me an invitation, I'll take somebody off so you can on.
Sure. Thank you, sir. Appreciate that.
OK，感谢。以后都是午餐就是聊啊，一直都是，然后都一直都是，这个接下来3、4。所以你明天还是不用去建文那边吗？
去帮我订了。
还好啊，对啊，那些孩子们也知道你不去，他们也不去。对啊，我今天顶谁？
Hello.
Very interesting.
Yeah, I try to make it applied, not just theory, and everybody get bored.
Yeah. No, very interesting.
Oh, thank you.
I know somewhere you can go to.
That's okay. I'll find it.
Yeah.
West.
听着好像有点
IT 一个学校。
The good old days. Okay. Anyway, all right. I'm good. I got your trip back there.
Hey, Danny, can you turn the air con up a little bit? It's so cold.
It's cool.
Huh?
You don't feel cold? No.
What's the low? 74 is fine.
70. It was 74. 72 is normal.
Yeah, how come it feels so cold?
All right, 75 if it works for you.
Oh, interesting. I thought it said 69 should be fine, but it was so
Maybe
cold.
you're sitting right next to the giraffe or something.
Oh, yeah. Mm-hmm. Wrong place. Next time I should wear long sleeves.
Maybe it's because you're wearing shorts.
Oh, that's good. So buy Amazon stock. 20 years, 20 years later, it will become 1 million.
20 years ago, it's $13, he just said, but right now it's $1,000.
1700 something per share. Amazon.
1700. No,
76 or something.
too expensive.
Yeah.
Nobody can buy it.
20 years later, it will become 117,000.
You don't have to buy a share. You can buy a fraction of the share.
Oh, okay. One share?
No, less
At least
than
I
a
have
share.
to
So
watch.
somebody didn't believe me on LinkedIn.
You see,
That's the max.
wow.
On LinkedIn, you can only have 30,000 first level connections. That's a lot. Way too much. Too many, huh? Well, and then I have 60,000 followers.
But he predicts the future and nobody knows the future.
That's why the future is unpredictable.
Yeah, unpredictable
Well,
in another way.
I've been doing this for a long
But you
time.
only look at the potential.
Well,
Look at the potential.
plus I knew the
Like the
developers,
media.
the founders of LinkedIn, so I was early on LinkedIn.
Yeah, I mean, before they got purchased, right?
Well,
Acquired.
I was number 512 on LinkedIn. So,
Yeah, that's good.
and I still get, let's see, what's my, I still have 1,700 invitations that I can't answer because I'm at the limit. And I get probably 10 or 15 a day.
You have to set up a second account. Reduction. Super low.
Oh, by the way, nice job.
Oh, thank you. Yeah, I mean,
No, you covered a lot of material
yeah.
very, very well, I think. And
Oh, thank you. Yeah.
And, I think it's going to help too, since a lot of people, haven't been through machine learning and everything.
Yeah.
I think
Yeah, I mean, it's good start, but then we go up the learning curve very fast. The first day is slow. Let's learn the basics, then you can go fast.
So ready for fast.
But some things are basic, so the basic stuff.
You're going to cover machine learning.
Huh?
You're going to cover some machine learning.
Yes. So we'll do some basic examples first, then we get into AI.
Yeah, 'cause I haven't had
That's all right. That's all right. I have 2 homeworks. I'll post it today, but it won't be due for 4 weeks. So because you will learn new things, then you can solve the problems. So if you just keep the document, right? I'll post it. Maybe you can do 1 or 2 questions, but then there'll be 10 questions in the homework, small and big. So by the time 4 weeks, you'll be able to do all 10. The first week, you can do maybe 2 or 3. If you're good, you'll do all 10. Yeah, why not? But I mean, my homework is not, is your thoughts, what you learned. It's not about just solving problems. Yeah. So,
will you set up account for all of us? Or
yeah,
okay,
I will do that.
Wonderful. Be in the past, oh, spend so much time.
Each of you will have your own account.
All right, thank you. Yeah. Hours.
Yeah. So you have some bad experience in the past?
Huh?
Some other class? You couldn't do that?
I mean, the previous class we spent so much time to just use some
Yeah.
or type or what it was.
Yeah. No.
So many issues.
You should tell Dr. Quinn.
I think I mentioned once that not was the time to really spend on those things.
Yeah, exactly. So I try to avoid that at any cost.
Much better.
Because nobody's going to ask you in the interview how you install. Because they will have it ready for you to do the job.
Yeah, Mac and Windows, they are different,
Yeah, cloud makes it very easy. Everything is containers now. Few dollars. It's $3 a day. Yeah. It's nothing. Yeah.
Less than a Starbucks.
Yeah. Yeah, if you go to Starbucks.
Yeah.
Like Dunkin' Donuts is taking over.
I have Starbucks beans and grind my own at home.
Really? You can use if you don't want to pay anything. Google has.
Do you have one?
Everybody's here.
So they have a website for students.
可以可以，这样。
Right. This is a free GPU cluster. The Jupyter notebook with the GPU. I'll show you.
Yeah. So let me show it to you. I'll send the link also in your Google group. One lady is missing.
Yeah, I think she went for a break. We don't see her.
I think she's the Dr. Glenn.
Oh,
I think you can put it in the chat of the Zoom.
Yeah, I'll do that. So this is the
I changed my background on my LinkedIn profile.
Why Google so generous?
yeah, I'll tell you about that.
The catch of AWS.
Yeah, so this is the GPU-based cluster from Google called collab.research.google.com.
It's a free GPU cluster. Okay.
So you can use this. This works very well. I've run it many times. I'll put this link on your on the group. Simple programs, you should be able to run it without any problem. So this is the link for my site. So don't put anything after this. Just put the first collab.research.google.com. What I wrote here. If you put other stuff, then it will open my book. But you may not have access to that because me. All right. So so this is the Jupyter notebook. It's free GPU cluster. You can change it to runtime, how you want to run it. You can do a command line if you want. So it will do a command line if you want. This is the command line here. You see code snippet. You can do table of content. You can create your own. You can add the code, text. It is very good because if you don't have a package, it will install it for you.
Mm-hmm.
Yeah. Right? So you don't have to install anything. So I'll paste some code and say, oh, Keras is not there. Okay, let me install it. It's like a bot, right? So that's the answer to Madam's question about Collab. Okay, so you can use this, but when we do our exercises, I will give you the AWS instance, which will be similar to this. But each of you will have your own. Because this one, she was saying why Google is so generous, because like what, Microsoft bought GitHub, $7 billion, because they want to know what you're doing, what code you're writing. So that's free.
Yes.
So that they can learn from that. And then they have this deep coder product. So it writes code by itself. So all your information will help them train that deep code engine so that it learns how to code. Yeah.
how about using Databricks?
And there are so many. There are so many out there. Databricks is good at Spark, right?
Uh-huh.
Yeah, in memory. But it's not free. Maybe it's little expensive.
Some version they have it is free.
But they may have a limitation. This doesn't have any limitation.
Oh.
It runs on GPUs and it's made for deep learning.
Oh.
So So yeah, so you can run any code you want. It will compile. It will detect it's either C# code or a Python code or any language you name it. It will learn. When you write, it will learn that you're writing a Java code or a Python code or any. It will compile it. Okay.
How about debugging capability?
It will do it for you.
It will do debugging.
But I mean, depends. I mean, Java gives kind of random errors. It's difficult to understand.
But we are more Python focused.
Yeah. So this is Python is very good.
Oh, yeah.
Okay. So that's answering her question. Let's go back to our learning. So let's say your manager comes and says, oh, I have this data. I want to build machine learning engine out of this. Okay. So what do you do first, right? So first you look at dimensions, how many columns the data has.
Mhm.
So the classic, like let's say you take Tesla's batteries, right? It throws out 50,000 parameters every nanosecond to the Tesla's data center. Okay, how the battery is performing, right? It's saying, okay, drainage, how much is drained? What is the next fast charging station? It's collecting all this data, right? An iPhone every 2 seconds sends logs to the cloud, okay? Every 2 seconds. That, okay, heartbeat, it's running okay, So we have 15,000 columns. So that's the high dimension data. Too many columns. Machine learning, you cannot have that many columns. It's called curse of dimensionality.
Yes.
Okay? Curse of dimensionality. So in curse of dimensionality, what do you do with that kind of data? When you have so many columns, you can't put it to machine learning. It will overfit. It will say, what the heck is going on? Like you said, garbage in, garbage out, right? It will overfit, and the model will be so inefficient. When you see the lift curve or ROC curve at the end of machine learning, that's evaluation. How do you evaluate machine learning models? It will say that you have 30% area under the curve. That's worse than a coin toss. Your results are so bad. So you don't want high dimensional data. So when you have high dimensional data, the 15,000 columns, you want to do topic modeling. You want to do probabilistic modeling, right? You want to do principal component analysis, singular value decomposition, latent Dirichlet analysis. So you don't have to worry about those names, okay? We'll talk about that. But you do these things to reduce the dimensions. So what happens is, let's say very simple process. You're boiling water, okay? Boiling water. So you put water bucket on the stove, and you start the stove. You increase the temperature. The water is going to boil. But then there are so many correlating factors, right? What's the outside temperature? What was the previous temperature of the water when you put it in? What kind of vessel it was? How much stove regulator? How much? All these are correlated factors. So you don't want to put all the correlated factors together in a machine learning model. What will happen is this collinearity problem. All the variables are all going up together. Then the model will be very bad. So that's why you need principal component analysis. So in linear algebra, the gentleman was talking about linear algebra in neural networks. So we all in high school, we learn eigenvalues, right? Eigenvectors, eigenvalues. So what does it do? So essentially, it's a mirror image of your data. So you're putting a mirror under your data, and you are drawing lines. Everybody is at the same level. Now I can compare between the two, right? So you're doing principal component analysis, calculating eigenvalues. So you divide the magnitude and directions, like a vector geometry, and you find covariance. Covariance, what is covariance? Covariance is essentially, let's say you have time, you're measuring something. Okay? So what happens is, something happens. So this is a covariance changing over time. So when you have parameters, right? This is a correlation. Right? It's a correlation with your correlation coefficient. Right? When you're correlating data, you're always going to get the same result. You don't want too many correlating data in your data model. Okay? So that's a problem we are trying to solve here. That's why you need principal components when you have too many columns in your data. So we'll go through many examples of that. Okay? Let's say you solve that problem and you have very few columns after that. You reduce the number of columns because you remove the ones which are correlated. Now you have responses. You don't have responses. Okay? Then it's unsupervised learning. So let's say all these cars sitting outside. I don't have any responses coming out of that. They're just some categories. So I want to know, okay, how do I describe a car, right? So I'm going to go to every car and answer maybe 50 questions. Is it automatic? Does it have air conditioners, right? Is it tinted glass? How many people it fits? What kind of gearbox it has? What kind of engine it has? I'm going to go to every car and collect all this data. And then I can do the clustering. I'm going to do the clustering where I can say, okay, there are 5 different categories of cars. There's the SUV, there's a sedan, right? There's a compact car, and a hybrid car, and luxury car, right? Maybe 5 categories. By looking at all those parameters, I can classify. I can cluster groups. Because I don't have a response, I can cluster it and understand what is going on. So when the iPhone came out, they did a survey of all the smartphones. And what do people want in a phone, right? They wanted to know what they want in the phone. So they come up with all the responses from people, like they want to do the email, they want to do a phone call, they want to browse internet from the phone, right? And they could build a device that can do all of that together. So that was an unsupervised learning, clustering, right? Market research uses that a lot. The different methods of doing clustering. Let's say you have responses. Does the response numeric, or is it a categorical response? Numeric responses are like, okay, you are using a system and it's giving you input and output, and it's continuous response. It's measurement, like temperature, pressure, you name it, right? All these are numeric parameters, right? And then you do this random forest, neural network, gradient boosting, and if it's non-numeric, you do classification on the left-hand side. So that's all classification happening on the left-hand side, okay? That's your supervised learning doing classification, okay? So you have 4 things you do in machine learning. Either you do dimension reduction, you do clustering, you do classification, or regression. 4 things. So if somebody asks you what you learned today in CSTU, you learned that machine learning does 4 things. Either it reduces dimension, it does clustering information, or it does classification, spam or ham, fraud or not fraud, right? Green or black, right? It does classification, or it does regression, building relationship between variables, okay? So that's the machine learning. So now let's go to Dr. Santiago Ramon, okay? So now this is deep learning we are talking about. We are done with background talks, okay? So now we get into the AI part of why we are here today. So 1899, Santiago Ramon, he fruit flies. Brain scientists, they look at fruit flies. They open it. It's the most primitive neuron model. So this they take out from a fruit fly, and this is fruit fly's neuron, right? So for like if you talk to Dr. Hinton, all his papers, you open his papers, they all talk about fruit flies. They try experiments on fruit flies. Same way, so they took the neuron from a fruit fly, they draw it here, as Santiago Ramon, right? And then Frank Rosenblatt at Cornell University in 1958, he said, okay, this is a perceptron. He said perceptron. He came up with the multi-layer perceptron. Okay, he came up with the word and he modeled it, and he published papers on that. Then came backpropagation from Dr. Hinton in 1984. That's what I'm telling you about. The Discover magazine talked about backpropagation in 1984, and it was an interesting time when backpropagation was very, very helpful at that time. Okay, so that showed the power of neural networks at that time. The 2010 was about recurrent deep feed-forward network. Dr. Bangio, sitting in cold Montreal winter, he said, okay, we're gonna try recurrent neural network and deep feed-forward networks. to make sure that we are able to understand sequences that happens in data over time. So let's say I take a photo of this class, and I take photo of this class every second. So can I predict what this class is going to do an hour from today? Then I do it every time. Every Saturday you come to the class, I take the photo of this class, and every second, right? So then I do it for 8 weeks, right? We're going to meet for 8 weeks. I can take a photo every second, 8 weeks. Then that's a sequence problem. So at the 9th week, I can predict what this class is going to do. You'll come at 1:30, they'll leave at 7, right? So all those things. Whenever we leave, right? Whenever we leave, 5, 6, 7, whenever we leave, right? That Dr. Glenn is going to decide that, right? So that's a sequence to sequence. So recurrent neural networks helps you do that, right? And deep feed-forward networks. So what happens is when we started learning neural networks, it was just 1 layer or 2 layers. But then Google found out in 2012 that if we put in thousands of layers, hundreds of layers, it can do better job, right? So that was 2012 onwards. We had multiple layers, and this is what we have. We have inputs, weights. Weights are nothing but slopes of a line. You fit a line on a surface, that's a weight. Then you have a neuron, right? It's just a y is equal to mx plus c. It's a high school algebra, right? Y is equal to mx plus c. Then you put activation function on the top of it. What does activation functions do? They are good for fitting curvilinear surfaces, okay? So that's the activation function. And then you have an output, okay? So that's the neuron model.
That's like John Nash's work in queuing theory.
Right, pretty much.
Yeah.
So this is our brain, and this is how neural network works, okay? So you have your inputs coming from nerves, all your nerves from the spinal cord. It's going up and telling what needs to be done. What the neurons do, they fit a surface to that information, okay? And then add them up, and then the synapse happens. Synapse happens, right? That's the activation function, okay? Activation, if you are a mechanical engineer, we do that. I mean, I worked a long time in nuclear power, and we would have heat exchangers. Very fast, the water is moving inside, and it's converting heat into steam, and then it runs the turbines and collect electricity, right? So that's activation, right? In neurons, its activation is you have activation function that will do the synapse. So it will fit the surface. It will fit a surface. It's a complex surface, because let's say I take a photo of a gentleman here. I take a photograph, and I want to know he is Dr. Lee Jones, right? He's Dr. Lee Jones. How do I determine he's Dr. Lee Jones? Because I need to fit his face on an existing surface that I already have, and compare the two, right? Same example is Google Translate. Yeah. So how does the Google Translate? Or how do you take a photograph on your camera and you post it on Facebook? How does it detect that your face, right? So if you take a photograph, what it does, it doesn't send the photograph to the server, it encodes it. Yes. So your photo becomes numbers, set of numbers, right? It's a hash, creates a hash. The hash gets stored in the cloud. And whenever you start your phone and start looking at Instagram, it decodes it at that time. So that's a snappy algorithm that compresses the image to 1/100th of the size. So the data center doesn't have to have that much memory to store, right? Same way we store these logs from the phones in the data center. We compress it. It's called snappy compression, Google snappy compression, okay? So
we created processing for data storage.
Right, exactly, right? So the activation function is essentially fitting. It fits complex surfaces, okay? So that's and then the terminal branch is the axon. So mathematically, Dr. Ng, Dr. Ng is the biggest neural network. He is teaching more students than any professor in the world today through deeplearning.ai. Okay, he is the biggest professor today, right? He's teaching most students any university, any online website. Okay, so he wrote this, he drew this, right? A lot of students at Stanford ask him, "Oh, Dr. Ng, you know, I mean, we don't know neural networks. I mean, it's very difficult to learn. We need the high level derivatives and calculus to learn." Dr. Ng says, "No, you do know high school algebra." Yeah. The students say, "Yes." Then you are ready for neural networks because it's brute force. You just need to know y is equal to mx plus c and a few line fitting functions to be able to learn neural networks. It's very easy to learn. If you know high school matrix algebra, you should be able to do this, right? And that's what it is. You have inputs, you have your weight, and you have your biases. You have to, because you don't want everything to pass through the origin. You need a bias. You know, that's how you control how the line fits, right? Bias is the way you fit, right? And then there's a variance, bias and variance. Everything we know today in our life itself, if you look at our life, it's all about bias and variance. And even in machine learning, it's all about bias and variance, right? So if you have bias, you have to optimize the bias. And then if you try to optimize the bias, then the variance goes out. That's a seesaw game, right? And then you have activation function. That's a function you apply on the fitted line to fit the curvilinear surface, okay? These are the activation functions, right? Sigmoid, 10H, rectify linear unit. So sigmoids are more 0 to 1, right? Like logistic functions. So like the best example of logistic function is the space shuttle that crashed in 1986, right? That space shuttle crashed because the O-rings of the rubber O-rings failed because they were not designed to work at 30-degree temperature, right? So when they designed that O-ring and they put it on the shuttle, they did a sigma. They fit a sigmoid function to that, and they said it works because they never tested at lower temperatures. They only tested at high temperatures, and this was an anomaly because the temperature in Florida is never below 50 degrees on that month. But it happens every so many years that the temperature was less than 50 degrees. And all of those things happened together and the space shuttle crashed, right? So that's the sigmoid function, right? Mm-hmm. So the professor who taught me gave me that example. I always repeat that. And it really sticks to your mind because that's a space shuttle. It doesn't crash every day, right? So 10H is -1 to +1, right? 10H function. And ReLU is a hybrid of the two. Okay, it works very well because neural networks, we always use rectify linear unit, right? So I was talking to this this person at Amazon Photos. Okay, so Amazon is coming out with the service, Amazon Prime Photos. Is going to be the most advanced photo sharing platform, right? So they are building it up right now, and they want scientists to operationalize it. Okay. So what that guy was saying, that question they asked me, like, what activation function you use to fit face recognition models? Because what they are saying is that that model will recognize any face in the world. That's what it's saying. It's a claim. It's a claim made, okay? But I don't believe that. But they claim that eventually, when it's operationalized, it will be able to detect any face in the world, right? So, and they are saying that 7 pixels are enough to detect a face. Yeah. You just need 7 pixels to detect a face, okay? So, yeah, that's also a claim. It's a claim.
Put me in the skeptical column.
Yeah. But that's a claim. I mean, you know, we always have put a stake in the ground and then you know, run for it, right?
Yes. Amen.
So I was asking one Intel scientist said, okay, you know, we are at 7 nanometers. We're going to 5 nanometer architecture in Intel chip, and how are you going to do it? Like, what next? What's next? Angstroms, you know? And they say like, oh, you know, every year we come up with a challenge and engineers build something better. So you know, so anyway, so the claim is always the case.
It's a 5 nanometer. It's the limit right now.
Exactly.
Yeah, after 5 nanometer,
Right. And then there was I looked at the graph. that the cost of development is going up. It's not a straight line. Now it's like the cost of development below 7 nanometer is so high, right? So deep learning, why deep learning is because the more layers you put in, the deeper, more complex surface you can fit. So with one neuron, you can fit a linear model. 2 + 2 neuron, you can fit a curvature. With 10 + 10 neuron, you can fit a very complex surface. This is very accurate, right? And when we talk, so like today morning, I was listening to music on my Google Home, and that I do in the morning, you know. So I say, Google Home, play this music, and I had an air conditioner going and a fan going at the same time, and I had the TV going on, and still I spake, and the Google Home could catch up right away, right? So how is it able to do it? Because it's able to fit a complex surface like this. Because there's so much noise going on around us, how do we get the signal from the noise, right? When you're driving, there's so many things going on, right? How does the self-driving car detect the object that's running across and stop, right? Because it has to do very, very complex surface fitting to be able to do that, okay? So that's a deep learning. So these are the three things: more data, faster hardware, right? And working ideas. This is your faster hardware, GPUs, right? GPUs, this is the GTX Titan, right? 7.1 billion transistors, okay? 4,500 gigaflops, 2688 CUDA cores. So in your AWS instance, when you start, you will see the power of this, right? That 7 billion transistors, how it's able to do brute force.
Moore's law.
Yeah. So these are the two papers that change everything. Dr. Hinton wrote this paper in 2006, and Dr. Bangio wrote this in 2007. And when Google implemented these two papers, the learning from those two papers and from in TensorFlow was come out of these two papers, essentially. Right? They programmed it out of C++ that was written by the students of Dr. Hinton. They essentially took the source code from his students, and they built TensorFlow on the top of C++ code that they had written, right? So it's 30 years of work. So fast learning algorithm for deep belief nets, okay? And greedy layer-wise training of deep networks. These two papers, if you can Google it and download PDF of this. So what this did, it explained regularization, because that was the biggest thing that was missing in neural networks at that time, before 2006. I took my classes 2004-5 time frame, 2002 2004, when I was in graduate school. And this work was latest at that time when computing was just becoming better and better. The memory was becoming cheaper and cheaper. And they were able to achieve regularization. So when we do regularization, without regularization, those models will run on your computer. But as soon as we add regularization, it requires 10 times the computing power, because you are imputing signals to avoid overfitting, okay? And stacked autoencoders explain how you can stack all these neural networks and for it to work, okay? So that's the stacked autoencoders. And you see this, this is the error rate, 30% error rate in 2010, right? Those are traditional neural networks. What happened in 2012, the error rate went from 30% to 16%. This was a breakthrough. Nobody could achieve this error rate, right? So I joined Qualcomm in 2005, and my boss gave me a problem. This is a TSMC fab in Taiwan. We had those packages. Chip packages we were building, and there was sealant. And he had like 5 million photos of all the chip being made. And he said, okay, can you measure the thickness of this epoxy? Let's run. And I said, okay, I can use MATLAB at that time. I could use some computer vision packages, and I could get to some results, which was okay. I couldn't successfully complete that project because the computer vision was not advanced at that time, and the image would go out of focus every time, and I will get wrong results. But if I would have had deep learning at that time, it would have worked. So I could get 30% error rate, 35, 40%, But 16%, none of the image computer vision application in 2012 could achieve that. And deep learning could achieve it. And that was a breakthrough. And you see, 8 layers means 8 layers deep. Yeah. So then it went to 8 layers. There was AlexNet in 2013. Dr. LeCun from NYU said, okay, I can do it with 8 layers. LeNet 11.7% because he put good regularization. Then came VGGNet from Google, okay? 19 layers. Then came GoogleNet. This was another point where Google Now and CD and Cortana were working very well. 22 layers, okay? Then came ResNet, 152 layers. This was ambitious, okay? Residual nets. Then came Ensembles, 200 plus layers. And you see the error became 2%. This is better than a human eye.
Yes, better than a human eye.
Right? So they could achieve this over time by increasing the number of layers. That's why it's called deep learning, because you go deeper and deeper and more layers and more features, okay?
But that means still, like trace recognition, then maybe they still can recognize one person. Still have errors.
Yeah, 2%, 3% error. Yeah, but
Yeah.
this is 2016.
Yeah.
Yes. So this is 2016. 2018 is 0.5%.
Mm-hmm.
Right? They achieved. That's like cyborg vision, right?
Yeah.
Right.
Is there such a thing as the overfitting if you?
Yeah, we'll talk about that.
Oh, yeah. Okay.
We'll talk about
that.
Yeah, there's definitely overfitting. So this is ImageNet competition. Okay, every year there's an ImageNet competition. Okay, somewhere in Hawaii or some European island, all these thousands of computer vision specialists meet, and they run this competition. 1.2 million images with 1,000 object categories. So 1.2 million images means that these are 1.2 million unique images and 1,000 object categories. So like 1,000 object categories means kitchen appliance, cars, airplane, dogs, cats, clothes, shoes, all these different 1,000 categories, okay? And this is 2012 when the traditional computer vision, like all these universities running it, Tokyo, Oxford, Amsterdam, they got 30%. But the LeNet got 16%. Everybody's like, oh my God, what happened, right? And that's when the whole tide turned. So now it's all deep learning. Nobody uses traditional computer vision anymore.
Yeah.
Everybody uses deep learning, right? Because those methods can't give you the results anymore. Easy to learn.
Is
right?
it similar with speech
Yeah,
recognition?
they're going there.
Oh, okay.
That's Microsoft, right? So, okay. And then, if you take all the images and videos on YouTube, on Google Images, World Wide Web, the biggest population of images are cat images. Most people have cat images, right? There are more cat images than any other image in the World Wide Web today, okay? Then comes, the second is cars. Then the third is aeroplane. The fourth is human being, person, okay? And fifth is chairs, and sixth is plants, okay? So that's how the deep learning works, because this is how abundance of images you get. So the best way, today, the best accuracy you can get today is detecting cats. The second is cars. Third is aeroplane. Fourth is human being, right? And high accuracy, okay? So this is GoogleNet. This is more than 200 layers of GoogleNet, right? So this is the background. I answer his question about speech, and same thing happened with speech, voice, right? And same time, they did a voice, and deep learning gave much better results than traditional machine learning. And you see, this is when the CD came out, 2011, right?
So Nuance is not doing this.
Who Nuance?
They're the speech recognition company.
Everybody's doing now. Everybody, see, look at this. To make speech recognition, it's a competition. You see, everybody switched to deep learning. All competition. They
From
moved.
NLP,
2014.
natural language processing.
Yeah. And you need NLP for everything. Okay. So these are the three guys: Dr. Bengio, Dr. Hinton, and Dr. LeCun. Right. They're all from East Coast. Okay. They have been working on. So LeCun joined Facebook. Hinton joined Google. Hinton is instrumental in developing TensorFlow. Dr. LeCun is at Facebook. So if you go to Facebook Engineering, you see his videos. And Dr. Benjo is at Microsoft. It doesn't show here, but with Maluba was his company. So
he's going to be speaking at the Microsoft event in Vegas next week.
Sure, why not? Right?
My daughter's going there. So.
Wow.
This is make Canada great again.
Yeah. And then, like I said, we are living in AI summer, which has been going on since 70s. Okay, so all this work we are seeing today, this is Dr. Goodfellow, Dr. Hinton, Dr. LeCun, and others, Dr. Rosenblatt. So all these people have done a great contribution to this area. Okay. So Dr. Hinton is great-great-grandson of Bullion, George Boole, Bullion Logic. He's great-great-grandson. Dr. LeCun is from NYU, and Dr. Bengio is from Montreal. So these guys he's good at platforms and Boltzmann machine and backpropagation. He's good at image recognition and LANet 5 architectures, and Dr. Bengio is good at recurrent neural networks, speech, NLP, chatbots, and so on. Okay, so these are the three things that are important, okay, to learn. So let's do some exercises now. Let's do some hands-on stuff, okay? So I'll go to a few things. So ConNet.js. The ConNet.js is Stanford. Dr. Karpathy, Andrew Karpathy, he joined Tesla last quarter, and ConNet.js, you can go to this link if you want, Google ConNet.js. So they say that these handwritten words are like fruit flies for neural network research, okay? Very, very commonly used. Any neural network paper you open, it has handwritten words, okay? So then you see it's a JavaScript library. It's running and it's showing this, number, and it's activation gradient, and then first convolution, rectified linear unit, pooled convolution, ReLU pool, fully connected layer, softmax, and you have the probability of detecting the object. Okay, so I mean, don't worry about the details. This is what the course is about. So we'll be talking about all the details of all these numbers that are changing here, and all the images, and what are these. But there was a question that some students asked me outside in the break that, okay, can you remove the features from inside, right? You were asking me about pulling the features from inside, right? So you can do that, right? These are the images that are happening at every layer. Okay, every layer, this is what's happening in the background, right? So every layer is detecting some details. Okay, so let's look at the other dimension of this. This is one dimension of it. Other side of the coin is this TensorFlow playground that the gentleman was using earlier. So this is the other side of the coin. So this is what happening inside. This is what the architecture is about. Playground.tensorflow.org. I'll put this on the groups so you have it. Here it is. Okay. The group is here. So I post a link on the Google group. Okay, this is your first layer, like how it looks, and second layer is this guy, where this is a very good um, handy link. Okay, so you can change the neural net. What the job here is circular pattern recognition. So you're classifying the blue and red, orange dots, right? So I can play it, and it will eventually classify the blue and orange dots. It's able to do that. Okay, so the TensorFlow playground can do that, and these are all the different parameters. That's what I call it tuning, hyperparameter tuning. Okay, these are all the hyperparameters.
Why was the spiral one down there?
Yeah, this one.
Yeah, that was the hardest one.
Yeah, so that one, the spiral one is the hardest one because it's alternating pattern, and it requires it doesn't have clear partitions. So when you do classification, you need clear partitions, right? But in this one, it's alternating. So what it requires special features that needs to be created for every orange blue change.
Okay, I don't really know much about this, but when I changed that tangent H to rect R's,
ReLU.
It learned it.
Yeah, because ReLU is fast. It's not always accurate, but it's very fast because it doesn't require it has a flat portion and then a very steep curve. Yeah, it's able to do much better. Okay. So, yeah. Right. Yeah. So we'll do a lot more. Okay. Let me show you something. Okay. And let me get that for you. So this is what classification does. Okay, so let me put this link up on Google Cloud, the cloud group.
I think classification just means grouping.
Yeah, I'll show you. Just give me a second here. So here, if you as you scroll down, it will help you understand how the classification work. Okay, so this is the visual machine learning. You can do English or Mandarin or other languages you want. So as you scroll through, it will show you how the classification work. This is the blue and green dots. Okay, So now it's doing classification. You see the partition you're talking about, that's creating boundaries. Okay, as soon as you create the boundaries, it'll start doing this type of correlations. You see how the dots are distributed across. And then as you move forward, it will show better boundaries. It will start to find boundaries here and to the first fork. First fork is like a pie chart, okay? Then you do the trade-off. Then you do the best split. And then you do the recursion as many times. And then what you are doing here is you grow a tree, right? So this is a binary tree. You're creating a tree, you see? It's doing the classification, right? I post the link on the thing. Okay, so this is doing classification now, right? A student like you created this. I'll show you the name, yeah. So then you're making prediction, you see? You make prediction, right? You make predictions. Once the model is built, this model is built. Now we are putting a production data in, and like you're driving to a Starbucks. Starbucks will know what you want to buy, right? So now you're doing predictions. So when a customer walks in, what the customer wants. So now it's doing the prediction, you see? Yes, then you adapt the model, right? That's why you need GPUs. You can do that many calculations. Then you do the reality check, do the training and then test. And then eventually you will get your results, right? So so these are the two students who did this. They built this page. Okay. Yeah. So this way you can understand it very well. So you don't need Python. You don't need nothing to understand machine learning. It's visual, and it's a perfect science. Yes. Yeah, but it's pixels. We'll talk about that. This is another interesting visualization for bias variance trade-off. Okay, so let me answer your question. So this does bias variance trade-off. It's very easy to understand how you can improve the machine learning models. Okay. Right. Okay. So so you can go through it on your own at your own leisure time, but I want to answer her question. Okay. So let's say how does it all work? Okay. So currently your phone can detect your face. Yeah. Right. Or if you have iPhone 10, it can do that. So these are all the models that are already built. So I put this link on the Google group. So these are all this is a basic network. So I can draw a 1 number and it will detect 1. You see, I can draw 2, detect 2. So it's going through a simple neural network and it's able to detect the number I'm writing here. You see, I can write number 3 and detect number 3. I can write 2 in my language and it will still detect it, right? So it's Hindi language, Indian language. Yeah. So so I mean, it can detect any number, right? 1, and then I'll put a 0 next to it. You say it's 0, right? Because 0 is dominating than 1. Yeah, I mean, let's try that.
That looks rather.
Yeah,
See, that looks rather like a
2
letter instead of a number, but
yeah, Roman 1. It will detect that.
yeah,
Roman 1. But it detected as 3 also. You see, some overshoot, right? It thought it's a 3 because it thought there's a line here, number 3, right? So this is a basic convolution neural network. So it took a while, but this is simple, 1s and 0s. Your pixels, let's take their image and divide them into pixels. Then your white is 0, black is 1. I can take all, let's make a 70 by 70 frame here. And every every pixel can be transported into the neural network. It will fit every pixel and detect, right? So like here, what I showed you, the playground, the TensorFlow playground, what is doing? What is it doing, right? I mean, I can do that. It may take some time, but what is it doing? Every neuron has a function to play. So I go to a simpler one. Let's go to a simpler one. And each neuron is fitting different surfaces. The first one is linear. First layer is linear. You see it's straight lines. Then the second is doing the features. The third is doing even deeper features. And the fourth is combining all of them together, pull it all together, okay? That's important to learn. And then this one is showing you all the different handwritten words, what exactly happens inside each layer. And what this is showing you, let me go to convolution VAE, and let me go to the GAN, okay? So this is, oh, sorry, ResNet. So I go to ResNet, and what ResNet will do is it will detect images for you, detect images. But to detect an image, you need a complex layer structure. So you can't run it with this type of simple structure like this. So what scientists have done, and you can pull papers with ResNet 50, what scientists have done is they have built the models that can be, this is a shrink wrap model that you buy from a store. It's running already, okay? So this is a ResNet. You see how complex this is. See how many layers? See, there are like 50 layers here. You see, it keeps going. So when you take a photo and put it on Instagram and it detects your face, it's running this type of network in the background, on the cloud or on the phone, right? So that's a ResNet 50, and I can select an image here. I can say like a bird, and it will take some time because it's passing the signals through all these layers, and eventually it will say it's a bird, right? See, hummingbird.
It's even a hummingbird.
Right? So, because these are pre-trained models, it has been trained on millions of images.
Yeah, how about people they wear hats?
Right.
They have
Right. So that's a good question, right? So what happens is we'll do a lasagna model later today, if we have time today, or maybe on Friday I'll show you. So lasagna model, what it does is it takes the main features, like the scientists have developed frame points. So what they have done is they take key features that distinguish you from the other person, right? So I have a North Indian face. So I have millions of people who have North Indian face, but they know that, okay, North Indian people, the two eyes are this much distance, nose is this distance, right? So they have built libraries on that. So it doesn't matter what you wear on you or glasses, as long as you get those points, it's able to distinguish you because you have unique distances. Right. Exactly. That's how it. So
the age also can change the face, right?
Oh yeah.
So how often do you need?
No, but then the pre-trained model like this, it has been trained on faces of different ages. So they always say that AI is very very biased, is because it's only trained on Caucasian men. So when I go to African American, it's very difficult to detect.
Yeah.
It's not able to do it. It's difficult, right? So then there are companies like Clarify, others, they are doing this on all different ethnicities.
Yeah, voice identification is interesting because I helped to study at Stanford because I speak multiple languages and I can do multiple accents, but it can still detect my voice.
Sure.
Even if I'm talking with a Southern accent, or if I happen to talk here with an English accent, like James Bond, it still can detect.
That's the beauty of
that it's my voice. Ich habe gehabt, musst du noch ein wenig sein. If it's in German, doesn't matter.
Right. So AWS has this. I just want to answer her question. So AWS has this commoditized packages that's running that running this Keras.js. It's running this this Inception v3. It's running that, okay?
Suspension bridge.
So you have this. It's detecting. It's object detection. So I can put in, maybe I take a photo of this class and upload it. It detect every object, a coffee machine, a table, computer, detect it. In this case, a scanned image is able to detect so many items. See, skateboard, sports, humans, people, person, parking lot, automobile. It's able to detect all the objects that are out here, right? Then I take a Seattle photograph, a Chicago photo. It will detect all these different objects in here. Now, let's say I want to do facial analysis. So like you were saying, somebody wearing glasses, it's able to detect it's a female, looks like a face, age range is very, very wide range, but it's an adult. Smiling, appearing to be happy, wearing glasses, wearing sunglasses, eyes are open, mouth is open, does not have a mustache, does not have a beard, right? So this one, it will detect 3 faces at a time. So appear to be male, age range smiling, appears to be happy, not wearing glasses. So I'm selecting this. Now I can go here and detect that. And then I can go here and detect that, right? So I can upload another image and it will detect that for me also, okay? Celebrity recognition, so Jeff Bezos, it will detect Jeff Bezos, right? Is another CTO, it will detect Andy Jassy, right? It will compare images together. This was a question asked to me from Amazon, right? They asked me, like, how would you compare 2 faces, right? What if the orientation of the face changes? How are you going to do that, right? And there are a lot of papers on this, right? But this one is able to do that. 98% similarity. Is able to crop the image and tell you, right? Same way, it's able to find this another image, which is different skin color. It's still able to detect, okay? So essentially, it is running this in the background, this Inception. It's running this engine in the background, right? Whenever you put an image, it will detect that for you, right? So this is recognition, okay? It can even get text in the image. It will take the text and say it's Monday, but keep smiling, right? So it's able to detect the even license plate numbers. I have a friend not too far from here, maybe just cross street. He works on ads. All McDonald's, when you walk into McDonald's, it shows videos and it shows items, right? Breakfast item, this, that. So it keeps switching. So people are watching, it's taking the eyes. There's a camera in the bottom. So it's saying, okay, how people are reacting when they're looking at that ad, because what they have seen that once they put more of a croissant or egg sandwich, people buy more of that because they want to see how it works. They keep changing that to see how people are reacting. So they have cameras in the bottom. They also do big jumbotrons. So they have cameras. They take the license plate numbers. Which car is coming again and again? Right? Who is watching at my ad? Right. That's how they count. How many people they charge money for that? Right.
Yeah.
So.
Google already has it. The Google page, they have camera on the page. You just upload the
Right. Yeah. So there are a lot of applications, but this is a commoditized because many of you are software engineers. So it's API. So you send an image as an API and you get the result, lat long, polygon, confidence, what it is, detection of the alphabets. It sends this back. If you have an application on your phone, you use AWS, they charge you 1 cent per 50 images, something like that. So it's a business model they have. So you have an API, you download the API, you put it in your application, then you send images, they will send you the results back. Then you can show it to your customer, what it is. Right? So that's the cloud commoditization. So people who use this don't know neural network, okay? So all these are like, you can download the SDK and use it. There's a pricing model. You can see the pricing, how much they charge in different data centers. It's 0.1 cent per minute for archived video analyzed, prorated to partial minutes, okay? So that's the business model they have. Okay. So then this one is still running. Inception takes a while. It has 200 or plus layers. So once it's done, you will see how long the layer is. You see how many layers it has. And one thing you can observe is a lot of repetitive. For Google Determined is that you don't have to have different layers every time you do convolution. You can have the same set of architecture, but repeat that multiple times. That's able to get more features than doing different layers. Okay, so that's the inception layer, and you can select an image here, and let's say a violin image, and it will go through all these layers, and it will tell me it's a guitar, it's a violin. Okay, so it takes some time.
An old one.
Yeah. So
Stradivarius.
it says it's a violin,
Corner of the mind.
right? It's able to detect violin. Okay. Yes.
You want to do, PCA to reduce the features, right? Then why do you repeat the features? I didn't understand.
Which features repeat?
Features will be repeated in different
No,
features,
I'll show you.
so-
Let me explain. So what is going on here? And this is little, we are jumping the ship, but I'll tell you.
Oh, I'm sorry.
All right. So let me just go through the right order, and I'll get that. Okay. So so what I was trying to show you was that these are all the widgets that you can use to learn how it works. Okay. So I shared with you the T3C3, the Asian guys who built that scrolling logic to learn classification and bias variance. I also shared with you the Keras.js, the Connet.js, the TensorFlow Playground. So all these tools are widgets for you to understand the concept we have learned today. Okay. So what is the biological correlation to this number of layers? Why do we care? Okay. Why we have number of layers? There's stacked autoencoders. That's a paper I told you that changed everything in neural networks, where the error went from 50% to less than 3%, right? So our brain, our brain is evolved from reptiles. We were reptiles millions of years ago. We still have that brain in our, that primitive brain, amygdala, they call it, the smallest brain. So amygdala is responsible for like extreme emotions like hunger, jealousy, anger, all those extreme emotions are because of the amygdala that we have. But then our brains evolved over time. So we developed prefrontal cortex that gave us sanity, audio-visual cortex that sees details and recognize objects. We can listen to music, all those things are audio-visual cortex. That's in the back of our brain here. So whenever we look at an image, it usually looks at the pixels first, and then does the layers, edges, and then goes to object parts, then goes to the object itself. It's going through all these layers and eventually detect an object. So it's going through all these parts of your brain. It starts from the spinal cord, then goes to the motor command, categorical judgment, high-level object descriptions. Then it goes to the simple visual forms, edges and corners, then intermediate visual forms, features and groups, and then high-level objects, right? So same way the neural network is designed, right? Same way neural network is designed, where you are going through these layers and eventually detecting an object. So how it does it? So let me explain it in detail. I have some handwritten things. Okay, so let's say you input a pixel through. So let's say I write a number 2 here. I write a number 2 here. I write a number 2. This is my 7 by 7. Okay. I write a number 2. Okay. I can divide this into 7 strings. Right? 7 by 7. And every pixel is 0 or 1. 0 or 1 or 2. Okay? These are all zeros. 1, 2, 1, 2, 1, 1. Wherever there's a letter, I have ones.
Like,
The rest are zeros.
can you just say one?
Yeah. Then what I do is I take this and serialize it. I take this and then put another one next to it. So I make this. No, there's no overlap. Okay. Okay, so I put all these cells in here. Okay. Then I input this into my neural network. Okay. And then it does this. Weight is the slope. It's fitting. I'm fitting a line through every pixel here. Every pixel, 7 pixels. Right? I'm fitting line to every pixel. And then I get the weight and bias. Bias, you need a bias in every fitting because you can't have all the points going through the origin. You need a bias. That's a bias. Then the slope, weight. Right. And then you have the activation function because I don't have linear lines here. I have curvatures. I need to fit the complex surfaces. That's the activation. Then I again do that again because what happens is first it will only get the edges. Then I want to make sure the edges are connected to each other. That makes an object, right? And then I do one more time. So I continue to do that. So it is able to detect different parts of the object at every layer. And it goes deeper and deeper and build relationship between them, right?
The bias is just some random number you pick.
Yeah, so bias is usually, so bias is intercept, right? Bias is an intercept. So because when you fit a line, you are trying, it's a brute force machine. Neural network is a brute force machine. So you are fitting a line, the slope keeps changing because the way the object is, you're trying all different ways, right? So like I was talking to you about Rubik's Cube, you're trying different ways, right? With the brute force machine, it's trying all different spaces and one of them fits.
But when you first start out, when you pick the bias,
Yeah,
some
random. Yeah. But then there are companies who are specialized in initialization because that's key. Because that will determine how long it takes for you to fit. So there are papers. Right now what people do is, Dr. Hinton has written many papers. They take the initial weights based on that, right? Because our categories are usually thousands or so categories of objects we see around here. So if you want to detect those objects, usually they are already given weight combination to start with, okay?
So for this case, this apply.
Yes. So I'll show you. That's a good question, right? So I have that in the ConNet.js. I have a complex surface where I'm looking at CIFAR 10. This is another Dr. Hinton's papers. It talks about, this is a sparrow, you see, and how it's able to do this, this particular activation. You see how that particular image is being, it's like a funnel. So that when you start, you have many more layers, many more neurons as you go down. Your form factor changes too. So when you start, it's as is form factor. But then image size keeps going down. You see, it's becoming smaller and smaller as number of layers goes up. And then you are doing, every time you have to do convolution, you have to do rectify linear. You have to do both fitting and activation, So you're doing this and then eventually you do a softmax, right? So every time you do a convolution, you have to do a pool because you want to combine the two information together. So I have some detailed slides. I'm going to go through it, but I want to make sure this is clear in your mind. And then eventually you do a softmax. What does softmax do? Softmax changes scores to probability because eventually you want to know how good you did, right? So you did all this fitting and then you compare with the ground truths and you want to know how good you did. So that at that time you want to do the probability. This is doing probability. This model is not doing so well. You see a lot of reds. So it's saying horse is able to detect, but the airplane, this is the frog. Others, it's not even able to detect. It's all red, you see? Yeah. So it's not doing so well. So then what it does back propagation. So get the signals and then do the back propagation to see how good the fit was. And then do that again. Keep doing that and improve the errors. So there's error optimization logic that runs at the end of the first forward prop. It's called cross validation, right? So there are different optimization models. The main one is called the gradient descent. right? Gradient descent algorithm. So there are different ADA boost or ADA grad, or there are many more optimizations that will make sure the error is optimized. Like gradient descent, it's used for that. Okay, so that's the let's go back to the theory here. So now you did a weight and bias, and then did a ReLU, rectified linear unit, then again weight and bias, and then softmax to get the zeros and ones. So the one is where is a good fit, or zeros are not. So when you stack them, you first do input, multiply, add, rectify linear unit. Again do multiply, add, rectify linear unit. Okay, and then softmax. Okay, that's the fundamental of neural networks. So that's the first. So you already built this TensorFlow playground. You already worked on that. I gave you the Keras.js, and so let's continue this this talk and talk about the architecture and hyperparameter tuning. But before we get to this, I have another set of slides I want to share with you. So as you said, we need a break every hour. So let's take a 5-minute break, and I will share with you those slides, which goes drill down into all the concept I just told you. Okay, so you will have better understanding of this. So then we etch it in our mind how it works. Then it's easier for us to understand it better. Okay.
Is there enough? Let's end with 5 or 7? No.
5. Okay.
Oh,
Fine. Sorry about that. There's a confusion. I thought we might go to 7.
No, we have 3.5 hours.
Okay.
Not 7. You are too energetic. Now you can see this. He want to plan to go to 7. No.
Yeah, they will only have 1 class a week.
Huh?
1 class a week, not 2.
We have a 2 classes a week. So right now, look like the students are more tired than the instructors. So.
No,
No, it's good. Very good.
I agree.
No, I mean, this is background. Today is background, right? Starting Friday, you'll be doing the work, right? So that's what I'm looking forward to. But you need some background information to jumpstart.
I just click your link. It's need the permission.
Really?
Yeah.
Oh,
Is that right? I click.
No, and if it's a Google account, it won't need permission.
I don't know. So let's try to see this.
Everybody is able to open it. Students are able to open the site. Yeah, because we don't have a Gmail account. If you log into a Google account, we won't need permission. This is the CSTU. Yeah.
So this is
yeah, because you went to my GPU instance. If you could click on this, just go to .com. This is my.
I know that's the link you sent.
Yeah, so I told them that don't do try after that. Just go on this good.com. I wrote it down on the board there. So this will work. This don't need permission. That's what's there. So I wrote it down here on the back.
Yeah,
because a lot of students.
In my office,
Yeah, no problem. Yeah. So let the students come back and we'll wrap up.
Yeah.
Thank you.
We probably can come back sooner, but we don't have that much
Yeah.
time.
So I will let them know.
Yeah. We only have like
50 minutes.
Yeah.
没有，我用你那个，就是根据他们生来的，从事小学送的，不是。就一个是 self， 还有一个是我是另外我也学过，那个怎么觉得？但是我用你这个，一个上课可能第二个
那你要说是来，我做解析学家的人，你要我做人，对，那你想要听我对那班什么看法？
我看好，快又开始，什么都是眼睛没有在，他没有在那么多，他自己
Real fine?
Yes, we are also fine.
No, we have both.
No.
You guys want to stay here? It's okay.
No. I mean, can I have another?
You guys want to stay? It's okay.
Unless you will need places after
I think you're based on chocolate consider and stuff.
You'll soon find out what happened because they see the pattern, that disappear.
Yeah,
disappear
my
from
junior
the
high national science
and they
fair
come to discuss,
project
right?
was a simple solution of non-Diophantine equations.
Yeah, that's
I think I stop at partial differentiation.
No, that's why I always paraphrase when people are talking and say, remember, I'm a mathematician.
It's fun.
Yeah.
I think this
Yes.
Yeah,
All right. So please have a seat. So I think we'll wrap up with 15 more minutes. So I wanted to just go through a few things before we stay apart. Okay. The display drivers sometimes. Yeah. So I'm going to share these slides with you. So these are all detailed on detailed slides on all the stuff we have talked about. So we'll go through it on Friday, but I want you to just study it based on what we have learned today. Okay, please study it because it goes through like a really good detail about every model and like what is the shape of the activation function, what equation represents, and how it really works. Okay, so it goes through like each component in detail, right? And it gives you an idea about every convolution layer, the neural network, the activation functions, the loss optimization, and what exactly happens when you are trying to detect X, right? So it took a long time for me to develop these slides. So just go through this in detail because it goes through every case. You see, it goes through every case, what I was drawing here, how it detects, what every convolution layer does, what does the ReLU does, right? What does the rectified linear unit, how does it work? So it goes through every pixel and gives you details about the formula and how the values are calculated from here, right? So what exactly happens, because this is what they asked in the interview, right? And if you bomb the interview, this is where you fail usually, because they ask you questions, one detailed question, and that's it. Once you answer that, then you are on board. No, you win their confidence. You know? One detailed, they'll ask you one or two detailed questions. Otherwise, you're just having a conversation. But if you're not able to answer the detailed question, the whole thing derails. Yeah. Right? So that's why I always emphasize that like detail is better when you're learning, right? And this one exactly helps you understand what exactly each layer does, right? Yes. So all the exercises I gave you, you try to correlate that with this content and see what you understand. And if you have questions, we'll go through this on Friday, but homework is important, right? So this is it's a whole use case on images, right? How does it work in detail? Like how does it detect that it's an airplane? Okay, so so just please go through these slides, and then I will share with you more of these on Friday. So what we covered today, just wrap up for next 5 minutes. So we started with introduction, and we built motivation on why we care about deep learning. We went through many industry use cases. What's the development? What are the startups that are in this area? What they are developing? What is AI? We defined AI. We defined intelligent systems. Then we went into details of, okay, what is first neural network that was designed by Santiago Ramon, and then Dr. Rosenblatt, and then Dr. Hinton, Dr. Bengio, and we went through the history of neural networks. We understood that how it all evolved from being a bad, high error rate, worse than a coin toss machine learning methods to state of the art today, and how it all changed over time for image recognition, for video, and for audio. And then we went into architecture of neural networks. So we did TensorFlow Playground. We looked at how the neuron is developed, different patterns, classification of red and orange dots. And then we went into Convent.js to understand what exactly happens at every layer. Then we went through Keras.js to see different CAN models that are out there, right? The Inception, the LeNet, the LXNet, and simple convolution. We went through all of that. I introduced with you this GPU-based free service from collaboresearch.google.com. It gives you access to a GPU cluster in the backend that you can use for free, right? It's available for free. We all can use it, and we'll be using it for all our programs that we run on Friday and Saturday next week. Then we went into details of convolution. We did all of the convolution layers. We understood how it works. And then we are ending here at hyperparameter tuning. That is very important. We'll talk about that on Friday. So this is all the hyperparameter tuning. And why do I care about variable types, scaling, cost function, different neural network types, number of layers, hidden layers, nodes, type of layers, type of weight initialization. There were a lot of questions about weight initialization. What happens when we start? Where do we start? What is the bias? What is the weight? So that's initialization. Type of activation functions, dropout rate, that's regularization. Then thresholds, that's the architecture. And then hyperparameter tuning is type of optimizer, like gradient descent, different type of ADA grad, ADA delta, and so on. Regularization rate, the type of regularization, then batch size, Nesterov momentum, decay rate. Yeah.
Yes.
Yeah, it's nostalgic, right?
Very nostalgic.
Right. Decay rate, momentum, right? How do we learn? How fast you learn, right? That determines how well you learn, right? Decay rate, how do you decay? What's the momentum? Type of fitness, like mean square error, accuracy, your cross entropy, epochs, stopping criteria. So all these are adjustments that are important to learn in deep learning. Okay, so doesn't matter you use TensorFlow, you use Tactiano, so many different things available. But if you know these things, because in the end you are going to apply, and these are the knobs you have to make your model better. And that's the key when you join a company as a research scientist or a data scientist working on deep learning AI problems. You are tuning these things, right, on different applications. I was telling you example of the electronic research lab, the Volkswagens that Apple is partnering with. So Apple is building a bus that will take them around the Apple campus. That is in collaboration with Volkswagen. So that's ERL, Electronic Research Lab, where essentially they take content and then create models like this. That works, okay? And then we will talk about different models. Like this is how the programming paradigm has been. So Theano is a Greek word, right? Theano is a Greek word for sharp tools. So that's Dr. Bengio has been doing that at the University of Montreal since early 2000s, early 90s. He's been developing this. And then came Berkeley at Cafe. Like you can go to Berkeley Vision project and a lot of demonstration of Cafe network. It's a pre-trained network. Okay, so Facebook uses that. Now they call it Cafe 2+. Okay, so that's a Cafe from Berkeley. Then Microsoft CNTK is more C#, C++. Then TensorFlow. So then Cafe 2 from Facebook. And then you have Keras, that is also from University of Montreal for research purposes. Then MXNet is from Carnegie Mellon. Amazon uses that. So all the demos I showed you from Amazon AWS, they were all MXNet. And then there's Chainer from Stanford, Dr. Socher at Stanford. He's working with Salesforce to develop AI-based CRM system, okay? That's Chainer. And then PyTorch, again, it's from Dr. LeCun at Facebook. And Amazon AI has combined all of these to make Gluon, right? So they call it a hybrid approach. So, right. Google is TensorFlow. So you have your symbolic, very difficult, efficient, portable, but hard to use, versus imperative, flexible, maybe slow, Cafe Torch. And you can combine the two together to make Keras or Gluon and other platforms. So we are not going to use, we are going to use pure TensorFlow for this class and Keras, okay? And
moving forward, we should be focusing on Gluon. Is that what it is?
I mean, if you are AWS person, then Gluon, then Google has its own layers they are building on Google Cloud Platform. Apple has its own ML Core ML, their own things, right? That runs on Swift and iOS. So everybody has their own flavor. So depending on, but if you know the concept, you can apply it anywhere, right? Because those hyperparameters are not going to change. The architecture is not going to change. It's how you implement it, okay? So if you want to do web API, it's more like the one I showed you, or Microsoft Brainwave or Oxford or CNTK, Google Cloud Platform, the web APIs. Then you have pre-trained models like Cafe from Berkeley, or MatComNet, or train your own model is Keras, Neon, Torch, or you want to design your own architecture is Theano, TensorFlow, Chainer. Okay, so depending on what you're doing in AI, you can choose the tools.
Right, for learning, do they provide content for learning?
Yeah.
Okay.
So, so along with the slides I showed you, these slides that I showed you, these slides, right? Along with these slides, I'm going to send you a set of textbooks, right?
Yeah, well, I mean, it's actually the content preparation that you were talking about.
Yes.
For the projects.
Right.
Like
So,
pictures or...
so there are two ways you can do that, right? So the ones we are going to use for the class are textbook stuff. So this is already embedded in the packages, okay? So like I showed you the ConNet.js, I showed you the MINT data set. The MINT data set is like a fruit flies for, so this is the, where is it? I was showing you that. So this is the MINT. Yeah, there's so many out there. There's so many. So MINT, there's Floyd, there's Kaggle, there's other platforms. So MINT is this data, MNIST. So any neural network paper you open today, it has MINT data. So this is already embedded in the packages we're going to use, like Keras or TensorFlow. They've already curated this and already there. So you can just use that. CIFAR10 is another data set that's embedded inside the packages. So this has all the different categories, like 10 different categories, like there's a horse and the boat will come, or cars. They have already curated it in a 12 by 12 pixel. So you can use it for training, right? But then when you go sophisticated, let's say you want to do faces, or you want to do dog faces, cat faces, you want to do all different applications. So there are a lot of things available on a textbook basis. Like you can buy that content, or you can use it open source. So like all these companies, like Apollo is from Baidu, right? But then Autopilot is another one. They already give you content. Like the German government, the Department of Transportation of Germany, has almost a petabyte of video and audio and photograph of roads and stuff.
NASA stuff.
Yeah, so then data.gov is another one. So yeah, so there are a lot of sources where you can get this information. But the like 80% of time is spent on making it ready for neural networks. Yeah. So there's a whole science on that. Right. Okay. So I will share with you. I'll share with you one book right now. We have 10 books in the end.
10
okay.
books.
But only 3 are applicable to this course. But I will share with you everything Dr. Glenn bought for me, so you have it as a ready reference. But we'll be using three out of the 10. One is called Deep Learning with Python. Then another one is called Long Short-Term Memory with Python. And the third is NLP with Python and Deep Learning. Okay, these 3 books we will use. So I'll share with you the first book right now. Okay, I don't want to get confused with the other stuff yet. We'll do it later on. Whenever we get to it, we'll send it to you. But I will share with you the first book, and we'll be using that as an exercise. So the books are written in very well. I think it's time. But the books are written, yeah. So the books are written in such a way that it's a teaching material. So it has code, explanation, and execution. So it doesn't have a lot of Greek symbols and equations. It's easier to apply.
You're going to send us links or
yes.
The book titles, because I can get PDFs.
No, PDF. I have the PDF.
Oh, okay.
The Dr. Glenn bought it is PDF, and also has code snippets. So it has one folder with all the code by chapter, and another one is a PDF book with 12 or 13 chapters. So we'll go through that in next Saturday's class. Okay. So yeah. So I'm glad. Thank you for your attention. We'll call it a day.
Really good. Excellent.
Thank you, Dr. Glenn.
Okay, good class.
The PPT will be shared on the classroom, or
I already shared on the Google
Doc, right?
group.
The group, yeah, group. Yeah.
Google group. I already shared, and I will also. So I will say I've shared with you a lot of things here. So Dr. Glenn shared the syllabus, and then I shared the material for day 1, and the collab, and Keras, and other links. And I will share with you the latest material, and go from there. Okay? Yeah. Yeah, that's already shared.
Okay.
It's called day 1 material.
Okay.
If you did not receive it, let me know. Thank you.
Thank you.
Yeah, excellent.
Yeah, if you have any questions, feel free to send an email on the group. Okay?
So the objective and outcome of this class is that you think we would have sufficient knowledge for like an interview, or
yes,
we need to do more?
So depending on what you do, right? So I mean, if you want to be a scientist, data scientist doing image recognition, like AI scientist, then you will need a lot more work, right? But if you are a statistician or a numbers guy, a programmer, a software engineer, and you want to get another software job or a hardware job, this will give you enough information to pass the interview. But if you want to be a subject matter expert in this area, then this is how I do it. I put my foot in the door as an analyst. Then I learn from colleagues. Maybe 5 years or 3 years from today, I will be the expert.
Sir, if I want to interview your team, like your team require the data scientist and also know like deep learning or just know the machine learning is fine. Because for my master degree is studying machine learning first, so.
Yeah, I mean, see, when you are the data scientist,
I am data scientist.
80% of your time you are curating the data.
Yeah. We did. I did the ETL and I did like the machine learning methods, but normally we use the statistics and machine learning together.
Right. So machine learning you apply maybe 20% of time. Most of the time you are preparing the data.
Yeah. So I just want to know if I want to interview your team, like what's the requirements, because I plan to
So if you have 5 minutes, I'll tell you. Okay. So let me go to that. I have to post that PPT link, the latest one. And also the book. Thank you.
Thank you.
Thank you.
Excellent.
Thank you.